Hello everyone. Today we're going to be looking at Physical Science paper 2 from 2023 November, the chemistry paper. Let's get right into it. So always the instructions, where appropriate, give your answers to 2 decimal places. Okay, but always remember when we're doing quantitative chemistry, so when we're dealing with moles and things like that, I normally like to work to 4 decimal places during the calculations and then final giving my answer to 2 decimal places. Okay, that should come up in this past paper, but let's have a look. Okay, question 1.1. They say give the name, so which one of the following name and formula combinations is correct? All right, so we're gonna have to know our polyatomics and things like that. So if we have a look, potassium dichromate. Okay, so this looks correct because the valency of dichromate is indeed 2, but the problem is dichromate. I mean, it's right there, for dichromate. There should be a 2 here. It should be Cr2O7. Okay, for dichromate. So this one is not correct. It's not correct. All right. Lead 4 oxide, so again the valency type stuff crossing is fine, but we always leave them with if they're common multiples like this, we always put them in the simplest form, the simplest ratio. So that is not the simplest form. Aluminium sulfide, so over here again sulfide, this is sulfite. So again, sorry, that's not correct, so we know D is correct. Okay, and we can also confirm. So I know it looks weird, right? But because you say, okay, where's the 3? Shouldn't there be a 3 here? Don't let that confuse you, right? Because the valency of chromium, they tell us in stock notation, is 3, and phosphate, we should also know the valency of phosphate is 3. So that's exactly how it would look over there. So 1.1 is D. Which of the following pairs of compounds will X have a higher boiling point than Y? All right, so when we're looking at higher boiling point, we're looking at the intermolecular forces. Okay, so we're looking, so if something has a higher boiling point, that means that it has stronger IMF, intermolecular forces. All right, so the thing on the left has to have stronger intermolecular forces than the thing on the right. Okay, so remember intermolecular forces, we have London, dipole, and then a special case of dipole, we have hydrogen bond forces of attraction. Okay, and another thing, well, you can see it's going to come up in B. So remember, all molecules have London forces of attraction, and London forces of attraction get stronger the more electrons a substance has, or a molecule has. So that means bigger molecules will have stronger intermolecular forces and higher boiling points. Okay, bigger molecules. So that comes up in B, for example. A lot of this IMF stuff comes up in organic chemistry. You have to know that longer chains, depending on the branching, but longer chains will have a higher boiling point, right? Because there's more electrons, more interacting surface area, stronger London forces, etc., etc. Okay, so we know B is wrong, okay, because this will actually have a higher boiling point because it has more electrons. Okay, so both of these are alkanes. It's just Y is what is that, 3 propane, whereas on the left we have ethane. So this one has more electrons. Okay, so it'll have stronger intermolecular forces because they both have London. Okay, X. On the left we have water molecules. Well, water molecules have hydrogen bond forces of attraction. Here on the right, H2S, I believe is dipole, but we know that it's not going to have hydrogen bond forces of attraction because remember, hydrogen bond forces of attraction come with NOF, nitrogen, oxygen, and fluorine. So even we know there's no hydrogen bond forces of attraction there. Okay, so this is not true. Okay, then over here, this is an interesting one. So we have CH3CH2OH. All right, so this is just some alcohol. It looks like ethanol. Here's another alcohol, sorry, but it's a diol. All right, because there's 2 hydroxyl groups. Okay, so I mean, you could draw this. So for example, here we have the one alcohol here on the left. So I'm not going to fill in all the H's, but the H's would be here. Okay, so that would be this compound I just drew. Okay, I'm going to draw this next one. Let me just erase some of this so you'll see clearer. So if I draw this next one, what you'll notice is so there the H's will be, here the hydroxyl will be, here's another H, here's another hydroxyl, and the H's would be here. Okay, so this is a diol over here. Okay, so this one here in C, there's actually two regions where hydrogen bond forces of attraction can take place. So yeah, so actually Y will have a higher boiling point than X, right? Because X is this one. This is X, ethanol, and this is the ethanediol, right? So it's not C. So it would have to be D in this one. But I've made a complete mistake of this. So the actual answer is A. But if we compare these two, if we compare fluorine and chlorine, well, fluorine has fewer, well, this diatomic molecule of fluorine has fewer molecules, sorry, smaller, what am I saying? It has fewer electrons than diatomic chlorine. Okay, so chlorine will have more electrons, so it'll actually have stronger London forces of attraction. Okay, so that's why it's not D. So my bad on that one. It's actually A over here. Okay, because hydrogen bond forces of attraction are stronger than dipole-dipole. Okay, some more hydrogen bond forces of attraction questions. So here we go in 1.3. Which one of the following diagrams does a red dashed line correctly show the formation of hydrogen bond between two molecules? Okay, so hydrogen bond. So this is actually kind of a definition you need to know. But so there's 3 bullet points you need for hydrogen bonds. So you need to have small molecule, high electronegativity, with at least one lone pair of electrons, at least one lone pair. Okay, so that's actually the formal definition of hydrogen bond forces of attraction. And we also know it's when hydrogen is bonded, it's hydrogen is bonded to something that meets these 3 conditions, right? But we know this is the definition we need to know, but for all intents and purposes, for our needs, we know that it's just when hydrogen is bonded to nitrogen, oxygen, and fluorine. Okay. When I say bonded, it's, okay. So you need hydrogen bonded to one of these, okay? Like for example, oxygen needs to have a lone pair that another hydrogen can be attracted to, not bond. Okay, so for example, we know it's not D. Okay, because hydrogen is not attracted to, well, it will be attracted, but yeah, this is not a hydrogen bond force of attraction, so it is not D. B, it is not that, because it's not when the hydrogens are attracted to each other. Okay, if we have a look here in A looks promising, right? Because it's hydrogen being attracted over here. But remember, hydrogen has to be bonded to one of these. It has to be bonded to one of these. And you'll see here, this hydrogen is not bonded to NOF. All right. So this is not hydrogen bond forces of attraction. Here in C, we have hydrogen bond forces of attraction. Okay. Because we have hydrogen, this one's bonded to an oxygen. We have this oxygen is bonded to a hydrogen. And this thing has lone pairs. Okay. That meets our conditions over there. Okay. All right. This is, I wrote it before, but this is what you need to know. This is from the SAGs. You need to know this as a definition, that hydrogen bonds exist between polar molecules in which hydrogen is bonded to a small atom of high electronegativity, at least one lone pair of electrons. Okay, but it's normally just enough for our purposes. 1.4, which one of the following graphs shows the relationship between the activation energy for a reaction and temperature? We know that activation energy is constant, okay? So it doesn't vary with temperature, so it just has to be C. Okay, this is a bit of a theory, but even if you do your energy profile diagrams and you do sort of one of these, okay, that drawing is probably not the best. It should kind of just straighten out there. But yeah, this is our activation energy. Okay, and it doesn't vary with temperature. It just varies if we have a catalyst. All right, a catalyst will lower our activation energy. Okay, even when we do our Maxwell-Boltzmann distribution curves, when we have something like this, the activation energy is always constant here. Okay, so it doesn't change. Like if, for example, if we increase the temperature, let's say if we decrease the temperature, our new curve will look like this. So, but you'll notice the activation energy is still here. Okay, so we have that. And here's the definition of activation energy. It's just the minimum energy required to start a chemical reaction. So it's a quantity. It doesn't change. Yes, we will have an increased rate of reaction because more particles have the necessary activation energy, but it's kind of just like a minimum requirement. Okay, it's kind of like if you go to a park, like an amusement park, it's like the minimum height to go on the ride. Okay, if you have more people there that are moving quicker, right, because that's kind of what happens with particles, it doesn't matter, you know, you still need to have the same height, and that height requirement is the same. All right, so that's what we have going on over there. 1.5, the certain amount of ICL. All right, so I is iodine in this case. Okay, so sometimes I use like I as like an unknown, but in this case we have iodine. So here we have this iodine chloride, it's sealed in an empty flask at a fixed temperature. The equation of the reaction takes place. Okay, what's important there? So it's balanced. They're given it as balanced. And it's also a reversible reaction. Okay, and they say which one of the following statements describes the changes that occurs as the system proceeds towards equilibrium? They say the rate of the reverse reaction increases, concentrations change at the same rate, the concentration of Cl2 increases. So it's important we need to see what we started with. So we start with a certain amount of ICL. Okay, so when they say that, they're implying that there's zero of this. There's none of this in our empty flask, okay? Because I say we start with a certain amount of this. They don't tell us anything about that. Initially, we know that the forward reaction is actually going to decrease. So if I do a graph of rate of reaction, well, I'll do the forward in green. So the forward will be like this. The forward will decrease. Forward will decrease. And what happens, the reverse, I'll do in a red. Reverse. The reverse will increase, okay? So the rate of the reverse reaction does increase. Okay, so this is again just from theory, but the reason the reverse increases is because currently when we have zero of these things, the reverse cannot take place. This cannot take place. But what happens is as we start getting more and more of this, we start going back, and these guys kind of just go together. It's almost like a snowball fight, I guess you could look at it. So initially these guys don't have snowballs, okay, but then this person starts throwing snowballs, and then now these two can keep throwing more and more back, okay, until eventually they reach equilibrium. Okay, so we know at least it is I. All right, let's look at double I's. They say the concentrations of ICL, I2, and Cl2 change at the same rate. Okay, so the concentrations of I2 and Cl2 increase at the same rate. That is true, right? And that's because they have the same balancing number, I suppose. But what happens is this thing is actually going to decrease at twice the rate. Okay, because you need two molecules of this to create one molecule of this and one molecule of that. So the concentrations do not change at the same rate. All right, and the concentration of Cl2 increases, and that's true. As the system proceeds towards equilibrium, this is true. Okay, because again, in the beginning we don't have any of this, and then we're starting to create this, so the concentration of that will increase. So 1.5 then is C. 1.6, they give the Kb values of two hypothetical bases are given below. So at this point we should be asking ourselves which one is a stronger base, and the number that is higher will be a stronger base, okay? Because this is the dissociation constant for bases, okay? But it basically just shows how strong something is a base, okay? So how easily it will dissociate. So we know that Y hydroxide is a stronger base because this number is higher, okay? They have the same scientific notation here, and you can see 5.6 is above 4.4, okay? So this is a stronger base. So they say aqueous solutions of the bases and their chloride salts are compared. All 4 solutions have the same concentration. Which base solution will have the higher pH? And which chloride solution will have the higher pH? Okay, so if we have a higher pH, as we go towards a higher pH like 14, that means that we are getting more basic. Okay, above 7, a pH of 7 is basic. Okay, so that is a high pH. So we know that Y hydroxide is a stronger base than this X hydroxide. So we know that the thing that of the higher pH has to be with Y. All right, so one of these. Okay, then they say the chloride salt with the higher pH. Okay, so this comes from, you have to know hydrolysis of salts. Okay, so basically what that's saying is we know if we disassociate this Y hydroxide, okay, we know that this readily dissociates. Okay, well, not readily, but it dissociates more than the X hydroxide, okay, because it's a stronger base. Okay, so this Kb tells us how forward favored this is. Okay, so when this happens, we're going to be getting this plus 2 hydroxide minus. Okay, so we know that this is very favored. It's more favored than X dissociating very similarly. Okay, so we know we were going to get more of this. That's why we knew it was going to be a higher pH. Okay, but if we look at the chloride salt solution with the higher pH, we know from theory that if we have a weak base, all right, if we have a weak base, its ions will undergo a hydrolysis reaction. Okay, so a weak base, their ions will undergo a hydrolysis reaction. So what that means, the ions from our X hydroxide, okay, so for example, if we look just at X, all right, X is 2 plus. If we disassociate, let me actually show the disassociation of X hydroxide. Okay, so it's also a two-way reaction where we have this plus 2OH minus. So we know that the forward is not that favored. Okay, we know the forward is not that favored because we know the Kb value is low. Okay, so we're not actually going to be producing a lot of these hydroxide ions. Okay, but the reason that is important is if we look at the hydrolysis reaction, so we take this ion and hydrolysis, we react it with water. Okay, and what we do, if we do this, we are going to produce, we know we are going to produce hydronium ions. Okay, we know it's hydronium ions because this is a positive, and we also form more of the, we form its base. All right, its base. Okay, so this is not balanced. So to balance it, we'll put a 2 here. And then in terms of hydrogen, that's 6. And we've got an 8 there. So this should be a 4. And our oxygens should be balanced, and they are now. Okay. The main point was not the balancing. Okay. The main point is this. We know that this has a low Kb. That has a low Kb. Okay. So what that means is it does not want to go this way. Not very much. What's more likely to go this way. All right, and it comes from this theory. If we have a weak base, this is our weak base. All right, we know it's a weak base because it has a low Kb. A weak base, it means that it's not going to dissociate well, but we also know that its ions undergo hydrolysis. Hydrolysis. Okay. So we know this is going to be happening this way, but I got this arrow. Okay, so what that means is we're going to be producing more hydronium ions, and hydronium ions are cause our pH to drop. So what happens is this this salt over here, if we have these ions over here, we know we are going to have a lower pH. So we know this is going to result in a low pH, whereas here these ions will give us a higher pH. Okay, so we have that for D. Okay, and again, it's because I haven't shown the hydrolysis reaction for this salt, but it won't really take place. So yeah, you can basically just, I wanted to give the full explanation here, but it's a lot easier to memorize. Let me actually just kind of give a summary for this. Okay, so if we have a weak base, that means that the ions undergo hydrolysis. Okay, we have that. And what we know is if we have a strong base, okay, it depends what it's combined with, but if we look at a strong base, we know that if we compare it to a weak base, we know the salt will be of a higher pH. Okay, this is only if we compare it with a weak base. All right, the salt will be a higher pH. So that's why here we have a strong base, and we know that its resulting salt will be a higher pH when compared to a weaker base. Okay, but there's a table you should remember where if you have a strong acid and strong base, well, that leads us to a salt that is neutral. So the salt is neutral. Okay. And then if we have a weak acid, well, before I explain what's going on here, have a think what will happen. If we have a weak acid, strong base, well, that's just going to leave us leave us with a salt that is a basic salt. Okay. And then there's a whole bunch of different combinations. Obviously here we can then have two weak bases, but have a look at your textbooks or notes, or whatever you use, should have a table that discusses this. Might also be in the SAGs. Okay, so yeah, I know I went in a lot of depth here, and there's a lot of, I didn't really explain this hydrolysis reactions properly, but I hope the summary kind of made things clear. Okay. So 1.7, we have an impure copper electrode, contains a small amount of gold and zinc. It's purified by electrolysis. During this process, a sludge forms beneath the anode. Okay, beneath the anode. Why is gold the only metal found in the sludge? Okay, so we know gold does not form ions. Okay, when we're doing this electrolysis and this purification, electroplating type stuff. And that's because gold does not want to be oxidized. It does not want to lose its electrons. It wants to stay as gold. It does not want to form, I think gold forms these ions. I'm actually not sure, but it doesn't want to go this way, right? So I'm not exactly sure of the charges, but gold doesn't want to form ions, okay? It actually just stays solid, right? So we know gold does not do that, okay? And the reason it's just not like it is basically just A, right? Because copper and zinc are oxidized, they lose electrons, but gold is not oxidized. Okay, so copper does form ions, okay? It is oxidized, it loses electrons, and so is zinc, but yeah, that's not what happens. And gold ions, again, gold does not form these ions because it's not oxidized. And it doesn't react with the electrolyte either. So this is just from a bit of theory. And then, for example, D, the amount of gold is too low, so it does not react. Well, it doesn't really depend on amount. It's just in terms of reduction and reduction potentials over here. But yeah, gold is not oxidized. It does not form ions in these electrolysis reactions. Okay, moving on a bit more. This is just this question is just pretty much pure theory. All right. So cations can pass through component X while anions cannot. Okay, which of the following might component X represent? So we need to know the different cells in the chloralkali process, and we'll know that the membrane is it does not allow cations. Sorry, it doesn't allow anions through. So we know immediately that component X is the membrane of an electrolytic cell used there. So it's in the membrane cell. The diaphragm cell does allow the anions to go through. That's why it affects our purity of the NaOH, the sodium hydroxide coming out, okay? And it's not the wire in the galvanic, and it's not the salt bridge in the galvanic. So 1.8 is B. Okay, 1.9, the alcohols form a homologous series. Which statement is correct? Alcohols have similar physical, chemical, same molecular, same structural formula. We know immediately that they don't have the same molecular formula and they don't have the same structural formula, because different alcohols will have different formulas, obviously, and different alcohols will have different structural formula. Okay, the molecular formulas will be similar and the structural formula will be similar, but they might have the same general formula, but they are not the same. They're not all the same. Right? Then similar physical and similar chemical properties. This is maybe a bit of a tough one, but you'll think, let's say you have a really long alcohol compared to a very small alcohol with a small chain. We knew, even from some of our earlier multiple choice questions, we know the bigger a molecule is, the stronger London forces of attraction will have, so the higher boiling point it will have. Okay, so they don't actually have similar physical properties. Because they're a similar group of chemicals, these alcohols, they'll have similar chemical property. They will not have similar physical property. Okay, so 1.9 is B. Then 1.10, red, brown, bromine water. So when you're seeing red, brown, bromine water, you must realize that this is a test for saturation. Okay, if we have an unsaturated compound where we have double bond carbons, we know that that will react with this red, brown bromine water and turn it colorless, all right, immediately, very quickly. All right, so we know for a fact we have unsaturated compounds, unsaturated hydrocarbon. So let's have a look. So unsaturated here, this is an alkene, Here they give a general formula of this. We should realize that is the general formula of an alkane. That will not cause this red, brown bromine water to decolorize. So the hydrocarbon undergoes a hydration reaction with bromine. So it is not a hydration reaction. It is not a hydration. It undergoes a reaction, but not hydration. Hydration's got to do with water. It's one of those organic reactions with water. Anyways, so even if you weren't sure about that, you can kind of just come back to D. But anyways, so yeah, let's actually do that. Let's say, okay, I'm not sure. It could be hydration. Let's just continue with the process of elimination, which is a really important technique, and I really do recommend it for multiple choice. But anyways, they say the red-brown color fades immediately in the presence of any hydrocarbon. That's not true. It won't do that in alkanes. And they say that hydrocarbon undergoes an addition reaction with the bromine. Yep, that's the type of reaction we had. Okay, but if you weren't sure if it's B or D, at least it's a 50-50 instead of a 1 and 4 now. Okay, but yes, the answer here is D. Here in question 2, they say the structure of solid sodium sulfite is shown in the diagram. Okay, so we got to maybe have a look at what's going on here. So it's a very interesting molecule. So we actually have in here, we know we have covalent bonds, right? Because they're both non-metals. Okay, but over here, this is a polyatomic ion with the sodium. So this is, and you can see we have these electrostatic charges of, electrostatic forces of attraction because of the charges. So this is actually a ionic substance overall. But if we just look within the thiosulfate, this thing's called thiosulfate, it's actually a covalent bond. So define electronegativity. So this is just what we got to know, a memorization thing. So they say a measure of the tendency of an atom to attract a bonding pair of electrons. They say in context, you might need to know it in context as well. You don't have to obviously say in context, but yeah, this is electronegativity. There's the definition of it. Okay, so a quick note about definitions. They count in each of your papers. So for example, in physics, it will count at least 10%, or very close to it, as well as for chemistry. So definitions are very important. Okay, because again, here we have another definition. Okay, describe a covalent bond. It's a sharing of at least one pair of electrons by two non-metal atoms. Very important, two non-metal atoms. Or you could say, remember this is just another part of the definition. You can say you don't need both. You could say a bond forming between atoms within molecules. Okay, I prefer this first one. The second one seems a bit vague, but anyways. So again, two definitions, and it's probably going to be a bit of a hint leading into the question. So we should be thinking about two non-metal atoms. All right. So which two atoms in this compound are held together by polar covalent bonds? Well, we know covalent bonds are what? When we have two non-metal atoms. Okay. So it's going to have to be happening here in our thiosulfate. Okay. But very important, I say which two atoms in this compound. So it's going to be the sulfur atoms and the oxygen atoms because they are non-metals. Okay, so we got to explain that. So they're both non-metals and they're bonded together. And the reason we also got to explain, so kind of saying sulfur and oxygen, it's a covalent bond because they're both non-metals, but we have to say why it's polar. So it's polar because they have different electronegativities, okay, versus non-polar where they have the same electronegativities, okay, because they have different electronegativity, or there's an electronegativity difference, okay, different electronegativity, negativity. All right, that's how you spell that, right? All right, electronegativity, where was it? Gonna bug me. Electronegativity. Yeah, there we go. Electronegativity. All right, I don't tutor English. I'm sure you guys can see why that is. Okay, 2.4. Question 2.4. They say an aqueous solution of sodium thiosulfate is prepared. What is meant by the term solution in the above statement? So again, this is literally just another definition, and a solution we should know is a homogeneous or homogeneous, depending, you can say it both ways, I suppose. Homogeneous mixture of solute and solvent. There we go, solvent. That is the definition for a solution. Then they say identify the solvent in the solution. So the solvent is the thing that you're dissolving something into, and it's aqueous. Aqueous comes from aqua, so it's water, or H2O. Okay, so the solute would be this. This is the solute, the thing we're dissolving in our substance over there. So name the bonds/forces in sodium thiosulfate, so the whole thing, that are broken or overcome when the compound dissolves. So the compounds are dissolving, that means their ionic bonds are breaking apart and they're forming ions. Okay, so it's the ionic bonds. Okay, all the forces, you could just say it's the electrostatic forces, and they also say, you could say the coulombic forces. Okay, but anyways, that's kind of easier to find electrolyte. So again, another definition, it's over here. It's a substance that can conduct electricity by forming free ions when molten or dissolved in solution. Okay, so we need ions. Is the solution an electrolyte? Answer either yes or no. So I forgot to put the mark allocation. This is, I believe, for 1 mark over here. So is the solution an electrolyte? Well, yes, because it forms ions, right? It's an ionic bond, and then it's being dissolved. So it is indeed an electrolyte. And here we go into question 3. They say solutions of sodium thiosulfate. We've already been working with this before, and hydrochloric acid react as follows. So you can see what's going on there. Luckily it's balanced. We know it's balanced because they give us the balancing numbers. I mean, I've never seen a question where they've put a number and it hasn't been balanced. So I have some students that always question. I guess they're a bit, I guess you could say paranoid, or maybe they just want to double check. But yeah, that's just a bit of a side note. It's most likely balanced if they give you numbers. But anyways, this isn't one of our normal type of reactions, right? Because you don't need to know. It's, when I say it's one of our normal type of reaction, I mean like when we have acid plus base is salt and water. Or if we have active metal plus acid, we get salt and hydrogen gas, for example. This is not one of those, right? Because we're getting sulfur dioxide and solid sulfur over here, which is very interesting. Okay, in question 3.1, it's another definition. They ask us to define reaction rate. So again, before we even answer reaction rate and before we go into 3.2 or the rest of these questions, probably reaction rate's going to be coming up. Normally it comes up right after, but otherwise it'll most likely be at least covered in question 3, something to do with reaction rate. But anyways, here we have the definition over here. It's the change in amount, you could say moles, or concentration per unit of time of either a reactant or a product. Okay, you cannot say over time. It's just a change in amount of moles or concentration per unit time of either a reactant or a product. Okay, so it's got a change in moles or change in concentration per unit time. Okay, not over time. Okay, but anyways, they say we're investigating now the effect of concentration of sodium thiosulfate on the rate of reaction was investigated. I kind of butchered that sentence, but anyways, in each experiment we have a volume over there. What's the problem with that volume? It is not in decimeter cubed. How do we convert? You had to divide by 1,000. Okay, keep that in mind because over here we work with decimeter cubed as an SI unit. Again, problems over there. Okay, so little things like this, and we got to identify them as soon as possible. Okay, but anyways, they tell us they give us here a volume and a concentration for what? HCl, hydrochloric acid. So what can we find with that? We can find the number of moles. That's probably going to be helpful. Okay, they give us a volume here of the sodium thiosulfate, and the results are tabulated below. Okay, so remember the square brackets indicates concentration. So there we have the concentration of sodium thiosulfate, and well, we know it's concentration because here's the unit of concentration, and here is rate. So rate is per second, all right, or just 1 over seconds. Okay, from our exponent laws. So we have that. Then 3.2, they now say consider experiment 5. So we need to be using these values. Very important. They put it in bold as well. They say consider that experiment in which the concentration of sodium thiosulfate is this. Okay. They say prove by calculation that hydrochloric acid is a limiting reagent. Do not round your answers. Okay. So let us have a look. So whenever we're doing limiting reagent, it's not that complicated. What we do is we just look on the product side. Sorry, on the reactant side, we calculate the moles of this, the moles of that, and then we compare. We compare what do we have and what do we need. Okay, so work out mole, then we choose one, okay, and we ask ourselves, okay, what do I have, what do I need? And then we make a conclusion, okay. If we have less than what we need, that means we have a limiting reagent. If we have more than what we need, our reagent is in excess. Okay, so that's basically how we tackle these. So keep an eye out for that as we do these problems. So again, we're looking at experiment 5. So let's work with sodium thiosulfate. I always like to label like this. It's good practice. Okay, so again, we need the number of moles. That's our first step when doing these limiting reagent problems. Okay, so we have C is N over V. Okay, we know the concentration, we know the volume. All right, so we have those values. We have to show substitutions here. So there we have concentration of sodium thiosulfate. The number of moles is what we're trying to find, and the volume is this, right? We have to divide by 1,000. Divide by 1,000. Okay. And when we solve for that, we get the number of moles for this is, it's going to be quite a small number. What you'll see is if we do it in the calculator, we're probably just going to, I prefer to leave it like this. Okay, 2,5 times 10 to the negative 3. Remember, we need a unit mole. Okay, you could technically do it with like 0,000. I don't like doing that. Okay. And they also say do not round. So if you did this to 4 decimal places, there would be some rounding, but I prefer use scientific notation. Okay, so we have the moles of that. We now need to find the moles of hydrochloric acid. Okay, very much the same thing. C is N over V. We know the concentration of hydrochloric acid. It's kept constant per, it's kept constant in each reaction. And here we have its volume, so that information was given here for HCl. Okay, when we solve that, we get N is equal to, so then again, this is going to be a small number, 0.15 times 0.05. Okay, so that gives us 7.5 times 10 to the minus 4 mole, all right, of hydrochloric acid. Okay, now that's our first step where we find the moles. Now our second step for limiting is we choose one and compare. All right, so what I'm going to do is I'm going to choose the sodium thiosulfate. Okay, actually, because they say we have to show that hydrochloric acid is the limiting reagent, I'll start with HCl. It does not really matter. It does not matter which one you do, but because I just want to do it the other way, but it will work out either way. So what that means, I'm now just doing a mole ratio between HCl and sodium thiosulfate. So I know the ratio is 2 to 1 from my balanced equation. It comes over here. Okay, and I know what I have is this. All right, so remember we compare what do I have to what do I need. Okay, so I have this many moles of hydrochloric acid. So what I need, sorry, not even what I need. So yeah, if I have this is how much of thiosulfate I'm going to need, sodium thiosulfate. So I take 7.5 times 10 to the minus 4, divide that by 2, and I get 3,75 times 10 to the negative 4. Okay, so this is kind of when we're doing our comparison now. So this is what I have of hydrochloric acid. If I have that much, this is what I need of sodium thiosulfate. So this is what I need. Now I have to compare to what do I actually have of sodium thiosulfate. Okay, and what you'll see is I have less. All right, so I have less than what I need, because remember this is the need. Okay, and here's what I have. This is what I have. Okay, using these values over here, not the rate but the concentration. So this is what I need, and what I have is less. Okay, so I need more than what I have. Whoa, okay, hold the horses. All right, sorry, this number is smaller than this number. Sorry, I thought it was bigger. Okay, sorry, these negative exponents mess me up a bit. So anyway, this number is smaller than this one. So what that means is I have more than what I need. Okay, so this is what I need, this 3,75 to the negative 4, and this is what I have. So this number is smaller, so I need less than what I have. Okay, so what we have then is, therefore, sodium thiosulfate is in excess. Okay, and then that means that obviously then the HCl is the limiting reagent. Okay, I kind of messed it up a bit, but I hope that was clear. And very interesting, my choice that I made here didn't give me, I wanted to get to this directly, but I had to first go through that step over there. So, but again, it doesn't really matter. Okay, but what we do is you have to compare what I need to what I have. I just messed it up because I didn't realize that this number was smaller than what I have. Okay, so I hope I didn't confuse anyone too hectically over there. In 3.2.2, they say calculate the number of sulfur atoms in the precipitate. This is important. In the precipitate produced when the reaction goes to completion. Okay, so technically we have sulfur atom here and sulfur atom there. Okay, but they just want in the precipitate, this solid, not in this gas. Okay, so we're just going to be looking at this sulfur over here. So first we're going to have to get moles. Okay, but very important when we're dealing with limiting reagents, we have to use the moles of the limiting. Okay, so we can't use the moles of sodium thiosulfate. We can't do a mole ratio with the sulfur. We have to do with our limiting reagent. Okay, So we know we are going to be doing a ratio between HCl and sulfur, the precipitate. Okay, the moles of HCl that I have is this 7,5 times 10 to the minus 4. So I write that 7.5 times 10 to the negative 4 is to, well, sorry, before I do that, I actually have to do the balancing numbers from this actual chemical equation over here. So it's 2 is to 1. All right, so that tells me then I just need to half this number, and that gives me 3,75 times 10 to the negative 4. Okay. So what do I have? What is this in terms of the units? This is moles. So now I have the moles of sulfur. Okay. So I have the moles of sulfur, but I need to find the number of atoms. So what I'm going to be using is I'm going to say, whoops, N is capital N over Na, where Na is Avogadro's number. Okay. So I know my number of moles of my sulfur atoms in the precipitate is this. I'm trying to find the number of atoms, and I know Avogadro's number from my formula sheet is this times 10 to the 23. Okay. I put that in my calculator and I solve that. The number of atoms is 6.02 times 10 to the 23. I get this. We're going to round to 2 decimal places, so it's 2,26 times 10 to the 20 atoms. Okay, you can say atoms of sulfur if you want. Atoms of sulfur. Okay, that's what we get over there. So what we can do is a sanity check. If you get a very small number of atoms, because we're expecting a lot of atoms. Okay, if you've done enough of these questions, you're expecting a lot of atoms. So yeah, if you're getting a very small, if you're getting like 5 atoms, then yeah, you're probably running into a problem. There's normally a lot of atoms. In question 3.3, we need to plot a graph of reaction rate versus concentration, and we need to draw the line of best fit. Okay, so here they give us the graph. We just need to fit in the graph. Okay, so they've given us a scale here on the x-axis, but for rate of reaction they have not. So we're going to have to make our own scale. So we're going to have to go up until 0.05. So if we count 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, that's a pretty good scale, I would say. So this is going to be 0.0, what do I say, 1, 0.02. Should probably write a bit thinner over here. 0.03, 0.04, 0.05. Okay, quite messy, but we'll make do. Okay, and what we need to do now is we've got this, and this is already have units over here. So now we just need to plot the points. Okay, so when our concentration is 0.01, that'll be here. Our rate will be exactly over there. That's quite convenient. Then when our concentration is here, our rate will be 0.09. So each one of these blocks is 0.001. Okay, so I'm sure you could figure that out over there. But anyway, it's over there. Then 0.4022. So here's 0.02, 0.021, and then 22 is there. We just count 2 blocks up from there. Okay, let me zoom in a bit. Okay, then we have a 0.08 and 42. So here's 0.4 and 4.2 again will just be 2 blocks up, and then 0.10, 0.05. Okay, so we have that. Okay, so now we need to do a line of best fit. We know they're directly proportional, so we know we need to start at, we need to go through the origin. But we need the line of best fit. So here we have like 2 points above, 1 below. This is 2 above. This is 2 points above, 2 below. So line of best fit looks something about that, I would say personally. That seems okay. We go through the origin, 2 above and then 2 below. That's probably a decent line of best fit. And then in question 3.4, they say determine how long in seconds. Okay, so that's important. we're going to have to give our answer in seconds, it would take for a sodium thiosulfate solution of this concentration to react in this experiment. Okay, so you might be thinking, what is going on over there? Okay, but let's refer back to our graph. Okay, so we can find the rate at this concentration. All right, it's not one of our tabulated values. Okay, you'll see our concentration of 0.03 is in between these. Okay, but what we can do is use our line of best fit. Okay, so we know I'm going to be using a dotted line over here. It will be about here, well, actually more here. Okay, so it's going to touch about there, and then we're just going to run that across from about there. So what I get there as if I read this value off from the left over here, I'm going to get, this needs to be thin. I get, so this would be 0.015, so this will be, I get 0.016 as my rate per second. Okay, so what that means is if I go down here, right, I get that the rate, all right, from my graph is 0.016, right, and the units here are per second. Okay, well, how do I go from per second to second? Well, I just need to inverse this. Okay, so I'll say therefore the time is 1 over 0.016, which is, if I put that in my calculator, I will get 62.5 seconds, okay, as how long it would take. All right, now they say state in words the relationship between the concentration of sodium thiosulfate and the rate of reaction. Okay, well, we have this table. Here we have the concentration of sodium thiosulfate, and here we have rate of reaction. Well, what happens to the concentration? The concentration is increasing. And what's happening to the rate of reaction? The rate of reaction is also increasing. Okay, so in terms of state the relationship in words, okay, I've skipped, yeah, I'll come back to that. But anyways, we're going to say that rate of reaction, here we have rate of reaction, and they're both increasing, so is directly proportional. Directly proportional to concentration. They now give us this graph over here. They say when the effect of temperature on the rate of the same reaction was investigated, the graph below was obtained. They say we need to use these values from the graph to determine the temperature rise required to double the rate of this reaction. Show your working. Okay, so you might be thinking, whoa, what's going on over here? Okay, but so what do we have to do? Here's our action word over here. We need to determine the temperature rise required to double the rate of reaction, double the rate of this reaction. Okay, well, let's have a look. So over here we have rate, and over here at this point here, the rate is 0.02. Okay, well, let's just see where it's doubled. Let's look at 0.04, and it's conveniently also a very nice number on the graph. Okay, so you can see here it's doubled. Okay, so what we do now is we just plot down from these values, and then we just get the temperature difference, because that will be the temperature rise. Okay, so we can say that what we're going to do is we're going to say, well, 52 degrees Celsius minus, and this will be 3678 minus 38 degrees Celsius. Well, that's going to give us 14 degrees Celsius. Okay, so over here you can just say, well, you would need a 14 degree Celsius temperature rise. We can say therefore 14 degrees Celsius temperature rise will double the rate of reaction. Okay, another possible, we could have also used 0.03 and 0.06. Those are also nice numbers. You would get the same answer. Okay, then this question over here, explain the effect of increasing temperature on the rate of reaction in terms of the collision theory. Okay, so we should memorize the bullet points. Well, you should memorize the bullet points for the collision theory. Okay, so we need to ask ourselves what happens when temperature is increased. Okay, so we're going to address that first. So we're going to say when, I'm going to write in shorthand here. So when the temp is increased, we need to ask ourselves what happens. Okay, so the temperature is increased, the particles have more kinetic energy. Okay, so the particles have increased kinetic energy. Okay, remember you're going to write in full words, full sentences. Okay, the particles have increased kinetic energy. Okay, so two things happen here. Two things happen. Okay, so this means that more particles, okay, this is now a second bullet point, more particles will have an kinetic energy greater than or equal to the minimum energy required for effective collisions. Okay, so I'm leaving out a lot of words here, but more particles will have sufficient kinetic energy greater than or equal to, so greater than or equal to, it's abbreviated over there, greater than or equal to the minimum energy required for effective collisions. Okay, so, and, right, we say, and there will be more collisions per unit time. So there'll be more collisions per unit time. Per unit time is an important thing over here. You need to be having this per unit time. Okay, so what we'll say here, I haven't seen this before. Normally over here we would just say therefore rate of reaction will increase. Okay, but what I see what the memo has done here is I say both factors increase the number of effective collisions per unit time. Okay, so at some point here, normally after saying there would be more collisions, we would say therefore, a normal bullet point will say therefore there will be more effective collisions per unit time. Okay, so more effective collisions per unit time. That's normally what we would say, but I see what the memo says here is that both factors increase the number of effective collisions per unit time, and then very interestingly they say the rate increases exponentially. Therefore the rate increases exponentially. I don't think I've seen this before, but I'll probably start doing that from now on. So when you increase the temperature, the rate increases exponentially, right? Why? Well, two things are happening. More particles have the sufficient kinetic energy greater than or equal to the energy required for effective collisions, and there's going to be more collisions because the particles have higher kinetic energy. They're moving faster. And then we can say then there's more effective collisions per unit time. But what I guess a new point is we can say that therefore the rate of reaction increases exponentially. Okay. So yes, you can memorize these bullet points. Okay, you should be memorizing these bullet points. When collision theory comes up, when you have to compare boiling points and discussing intermolecular forces, these are things that come up all the time. Le Chatelier's principle comes up all the time. You shouldn't really be doing much thinking. Okay, you just memorize the steps, memorize the bullet points. I know it's not nice, I know it's not fun, but it gives you an easy 4 marks. Okay, and comes up all the time, guys. I know it's not the funnest, but it comes up all the time. All right, so I know those bullet points. They now give us this equation. It's a hypothetical equilibrium reaction. All right, so we got some solids on the left with a gas solid and a gas on the left, and that just gives us a gas on the right. They tell us that the reaction is exothermic. All right, and they give us the equilibrium constant, and they say at 40 degrees Celsius. They say, why is the temperature specified? Okay, sorry, this is also question 4, by the way. I didn't include that. This is question 4. We just finished question 3, so this is a new question here. So they say, why is the temperature specified? Well, we know that the equilibrium constants constants, my spelling, let me just copy from the memo, constants are temperature dependent. Okay, that's the only thing that affects our equilibrium constants, temperature. It doesn't matter how much of this we start with, we start with concentrations, everything will keep it the same. Even if we add a catalyst, everything will happen, the Kc will be the same. All right, our reaction will happen faster if we have a catalyst, but the equilibrium constant is constant unless you change the temperature. Okay, so that's why we have to specify at a certain temperature. Okay, now they give us the reaction again and they say write the expression for the equilibrium constant for this reaction. Okay, what we have to remember very importantly is constants are not included in our equilibrium constant expression. Okay, so, and remember we have the concentration of the products, okay, with its balancing number up here, so it's just the one in front there, so I'm not going to include this one here. Okay, we have that over the concentration of our reactants, but only the gaseous reactants. Okay, and the balancing number here of B is 2, so that's why this is square. Okay, but this is not here, this is a solid, so it does not appear in our equilibrium constant expression. Okay, does not appear there. All right, so this is our Kc value, well, expression. They now say that we have that much mole of B is added to 2 decimeter cubed reaction vessel. Thankfully, our volume isn't decimeter cubed. Always keep an eye out for that. The container was sealed, allowed to reach equilibrium 40 degrees. At equilibrium, there were X moles of A3B2 in the container. That's on our product side. Use the Kc expression to set up a mathematical equation that can be used to solve for X. It's not necessary to simplify or solve their equation. Okay, so this should be in your minds. You should have a little bell ringing, ding, ding, ding. This is a rice question, a rice table question. So if you don't know what a rice table is, maybe you know it by a different name, but you should be knowing how to do these tables. You can see it's for 5 marks. Okay, so rice, you'll see what it stands for. I'll explain it. Okay, so we have R. So R is for reaction. All right, I'm going to write our reaction. We have 3A, it's a solid. I'll put this over here. We got 3A as a solid plus 2B as gaseous, and that's in equilibrium with, and we have A3B2 also gaseous. Okay, so that's part of our reaction. Now we say initial, and we can do a rice table on a mole basis or concentration basis. I'm just going to do a mole basis, okay, because they give me this in moles and then they said this moles, so they gave me moles. I'm going to do it moles. Okay, so initially moles. So first of all, this is a solid, so actually what we do in this column, we don't care about any of the values. Okay, anyways, they say initially we have this number of moles of B is added, so this is what we initially have of B. Okay, they don't mention anything about this. Okay, so that implies that there is 0 of this. Okay, comes up all the time. They don't often tell us this, but it means there's 0 of that. It just means we added this, we didn't add this, so there's 0 of this. Okay, so you can safely assume that. Okay, I know it's confusing, but you have to get comfortable and just saying, if they just tell me this, that just means there's only this and 0 of this. Okay, some of my students don't feel comfortable making that assumption, but if you practice enough of these, you'll see that you do make that assumption and it's safe to make it. Anyways, they say, okay, what's next is our rice. So we got RIC. So C stands for change. Okay, C stands for change. Also, what I'm going to do, I'm going to change this color over here just so it's a bit clearer for us. So initial, we have this many moles, and over here we have that many moles. Then change. We now need to see what the change was. Okay, so they say at equilibrium there were X moles of that in the container. So they don't tell us what the change was, but they tell us our last part, E. E is for equilibrium. So R reaction, I initial, C change, E equilibrium. So they tell us the number of moles at equilibrium of what? of A3B2, this thing. We know at equilibrium there are X moles. Okay, so what was the change? How do we go from 0 to X? Okay, so what I like to do also, I like to do something like this, okay, because you'll see it's almost like a little math equation over here. 0, right, and we're getting more of these things, okay, because we know we're getting more of this because initially there was 0. So also, how do you go from 0 to X? You have to gain X, okay, so this positive over here is important. All right, and now what we have to do is we have to do a mole ratio, okay, so this is 2 to 1. All right, so this is also a big reason why we write this reaction, okay, over here. We have to use these mole numbers over here. Okay, so if this thing gained X, this thing had to have lost double that. Okay, because you need 2 moles of this to create 1 of that. Okay, so say for example this thing gained, let's say this thing gained 0.1 moles. Well, then this thing had to have lost 0.2 moles. Okay, because 2 moles here creates 1 mole there. Okay, anyways, so that's how we get negative 2x. Okay, and what we do now is we just add this column. Okay, so we just say 0.3 plus negative 2x. Okay, because we're adding down here, but that's the same as just saying minus 2x. Okay, that's why I like to put this line here. Okay, so E, this is the moles at equilibrium. Okay, but when we go into our equilibrium constant expression, we're going to need concentrations, right? That's why we got these square brackets. So what I have to do then, not that over there, it's a bit far, I have to now work out the equilibrium concentrations. But that's quite easy because what's my volume of my container? That. Okay, so I'm just applying this formula over here where C is N over V. So here I have my equilibrium moles, but now I need my equilibrium concentration. So what do? I take moles over volume. So here's my moles, 0.3 minus 2x, and then I just divide my moles by my volume. Same thing over here. Here's my moles, divide by my volume. Okay, so there you have it. There is my rice table done, but very important, I have to use the KC expression to set up a mathematical equation that can be used to solve for x. Okay, so I'm going to go back to this thing, all right, but I'm going to have to sub in here. All right, so I'll copy this over for us because we are going to use it. I'll pop it here, move it across. Okay, but what's interesting is we know what KC is. Well, because they told us, they say it's 1,65. So I'm going to say 1,65 is equal to, and now what I do is I substitute in my concentration of this A3B2, which is this. So I say x over 2, and that whole thing is over B squared. Here I have B, the concentration of B. So that's over 0.3 minus 2x over 2. This whole thing is squared. I now have this mathematical equation I can use to solve x. It's quite complicated to do the maths, well, relatively complicated, but I have the expression. So that's what they need. All right. Now they say that they rewrite our equilibrium reaction here, and they say simplifying and solving the mathematical equation obtained in 431, this thing over here, they say they gives 2 answers for x, and they say the number of moles of A3B2 at equilibrium can either be these 2 things. All right, and they say explain why this value is impossible if the container originally contained that many moles of B. Okay, a few different answers we can say here, but let's look at our rice table. Okay, so we have to explain why this is not possible. Okay, so it's 0.56. All right, so if you do 2 times 0.56, if you do that, you're going to get over 1 mole. Okay, it should be 1,12, I believe. Okay, but the thing is, we started with 0.3, and if that x value, if we sub it in over here, we are losing 1,12 moles. But it's impossible. If we had 0.3, you can't take away 1,12. That just doesn't work. Okay, so there's our explanation, right? You can literally just say that, well, if you take 0.3 minus 2 times 0.56, right? If you do that, we actually get an answer that's less than 0. Okay, so that's literally your explanation over there. Okay, so, or you could, there's a few different things. Let me actually just copy over what the memo says. Okay, here's a few things from the memo. So the memo gives this statement over here, which I've put there. Or you could say there's not enough B to produce this amount of A3B2, which I guess is already stated here. And they say the ratio is 2 to 1, or you would need that many moles of B. Okay, initially, something like that. Okay, yeah, initially. So yeah, this is also true. The maximum amount of A3B2 possible is 0.15 mole, not this. Okay, so a few different answers you could do over there. Okay, so yeah, if we're starting with this much initially 0.3, the maximum we can do is use up all of this, okay, to then create this thing's over here, but it's in a ratio of 2 to 1. So the maximum you can have here is 0.15 for X, the maximum, if all of this is being converted into A3B2. All right, that's the maximum X we can have. Okay, so a lot of reasons you can say over there. Now they say calculate the equilibrium concentration of B in the reaction vessel. So the equilibrium concentration of B, well, we know it's this. This is our expression for the equilibrium concentration. Remember, concentration is in square brackets. So we know it can't be this, so that we're not going to plug in that X, we're going to plug in 0.04 for our X. And so we're going to say 0.3 minus 2, 0.04 over 2. Well, we can say concentration is equal to that. And if we put that in the calculator, 0.3 minus 2 times 0.04 over 2, we get 0.11 mole per decimeter cubed. Okay, don't forget your units. Not worth losing a mark for forgetting your units. Now, in question 4.4, they say the reaction is repeated using a catalyst with all the other conditions remaining the same. Circle the correct option between the brackets. All right, so the Kc value, the value of Kc will increase, decrease, or stay the same. What is Kc dependent on? Only temperature. Only temperature. Where did we discuss that? 4.1. Equilibrium constants are temperature dependent. So that's the only thing that will change Kc. So if we're using a catalyst, it's going to remain the same. Let's circle. Okay. The value of delta H, which is our enthalpy, remember that's just the energy released. This also remains the same. It does not change that. Okay. It does not change that. Remember from your energy profile diagrams. Right, so that's without a catalyst. What the catalyst does is it just lowers the activation energy. It just lowers. So we're going to need lower activation energy. Okay, but we still end up at the same energy of products. Okay, so hope that makes sense. 4.42, the graph of the original reaction rate versus time is given below. On the same set of axes, draw the graph to show the effect of using a catalyst from time t equals 0. Okay, so if we use a catalyst, we know two things, all right? So if we're using catalyst, what happens? It speeds up rate of reaction, forward and reverse equally. So it speeds up, I should really have said increase, but it speeds up rate of reaction. Okay, increases rate of reaction. So what does that mean? We know here our rate's over here, so we need to end up at a higher point. Okay, because it increases our rate of reaction. What it also does, so it increases both equally, forward and reverse. But what that means is we're going to be reaching equilibrium faster. Equilibrium will happen faster. So the way this will look is we're going to be reaching equilibrium faster, and what will happen is we're going to end up at a higher rate. Okay, so it should look like this. All right, so there you have it. The rate is increased, all right? So we're at a higher value than what we were before, but we also reach equilibrium faster. So we go parallel faster, because remember, when the rates are equal, that's when we're in equilibrium. Okay, so those two things over there gives you 3 marks. So what's important is the initial rate of the forward reaction is faster as well. So that means we don't start here anymore, we start higher. Okay, so we have that going on for us. Next question. They give us the reaction again, but it's now carried out at a lower temperature. Very interesting. Okay, no, they just give, it's the same Kc value because they're just mentioning it at 40 degrees Celsius. So let's not worry too much about that. They say we have to circle the correct option between the brackets. All right, so now they say the yield will increase, decrease, or remain the same. All right, so when they're talking about yield, they're talking about the concentration of this. So we need to be talking about we need to be thinking about, is the forward favored? Yes or no? All right, so we need to think about, well, the forward reaction is, if we're looking at temperature, we need to be thinking about exothermic or endothermic. The forward reaction is what? Exothermic. We know that because of this enthalpy. Okay, so the forward reaction is exothermic. So if we decrease the temperature, what's going to be favored? That means the forward will be favored because that's going to increase our temperature. Okay, it's going to relieve the stress. All right. So if the forward reaction is favored, that means that the concentration of this will increase, or the yield of this will increase. So that's why it increases. And 452, they say you're going to have to explain your answer using by applying Le Chatelier's principle. Okay, so again, we're going to be applying bullet points that we'll memorize. Okay, should be memorized. Okay, we discussed it briefly. Okay, but we need to be saying that the stress on the system is a decrease in temperature. Okay, so we have to identify the stress. So we'll say the stress we'll just say that the stress is a decrease in temperature. All right, so we need to be saying how we're going to be counteracting the stress. Okay, so the system, we should say therefore the system will want to increase temperature to relieve the stress. Okay, so you need to be saying this point that the stress is a decrease in temperature, because we need to be saying, okay, we want going to increase the temperature to relieve the stress. Okay, so you do need to talk about stress over here and then relieving the stress. I'll explain the bullet points after we're done going through them. Okay, so we have that, and then we say therefore the exothermic reaction, so the exothermic reaction will be favored as it increases temperature. Then we say, okay, well, what is that? Is that forward or reverse? And we say, therefore, the forward reaction, how did I spell that? Forward reaction is favored. Okay, now we just need a conclusion. Therefore, yield will increase. Okay, so let's just break this down. When we're answering these Le Chatelier's principles questions, you have to identify the stress. Bullet point 1, ID the stress, identify the stress and state it. Then step 2, we say how we counteract. How counteract. All right, and then we also say relieve the stress, relieve the stress. So we say if we have a look here, we identify the stress, it's a decrease in temperature. Bullet point 2, this was our first bullet point. Bullet point 2, we're saying how we're going to counteract by increasing the temperature. Why? To relieve the stress. This is important. Relieve the stress, you need that. Okay, bullet point 3, we say what is favored. Okay, so in terms of that, so what will be favored? So how are we going to counteract that? By doing what? So the exothermic reaction is favored because it increases temperature. Okay, and then now we say forward or reverse. Okay, so what is favored? For example, when we look at pressure changes, say for example you decrease pressure. All right, well, so that's our stress, decrease in pressure. What's the system going to want to do? The system will want to react to increase the pressure to relieve the stress. And then we say, okay, what reaction will do that? And we'll say then the reaction that produces more gas molecules will increase the pressure. Then we could say therefore the forward or reverse, depending on the type of reaction. It doesn't matter in this one because they don't ask about pressure. And then we'd make a conclusion. So that's kind of what I mean there by what is favored. Okay, so it's linked to the stress. All right, and then we said the forward or reverse is favored, and then 5, we make a conclusion. Okay, so this is the process for Le Chatelier's. Okay, then 453, just down over here, it's a bit hidden. They say the value of Kc, will it increase, decrease, or remain the same? All right, so what Kc is temperature dependent. Okay, so don't fool you. Here is just Kc at a certain temperature. They're just saying, okay, well, at 40 degrees, we know Kc is that. But we know Kc is going to change because there's a change in temperature. So it will no longer be this. Okay. But anyways, we need to think about, so when Kc gets bigger, okay, so when Kc gets bigger, that means that the concentration of products is, so yeah, when Kc is bigger than 1, that means the concentration of products is greater than the concentration of the reactants. Okay, that's just from the formula, all right, of Kc. So we know that the forward is favored, so we're producing more of this. So the concentration of this thing is going to increase. So if the concentration of our products increases, that means that Kc will increase. Okay, so we have that over there. Okay, because remember the equation for Kc, you can have a look, but the equation for Kc is literally just the concentration of the products and their balancing numbers over the concentration of the reactants. So if we increase the concentration of the products, obviously Kc will increase, and then vice versa for reactants. If you increase the concentration of reactants, Kc will decrease. Okay, so Kc just tells us where equilibrium lies, more or less. Okay, so bigger Kc, forward favored, lower Kc, reverse favored. For question 5, they say solutions of a hypothetical weak acid H3A. All right, so very important, it's hypothetical. So obviously we don't have element A on the periodic table, so it's just a hypothetical weak acid. So it's a weak acid, that's probably important. And sodium hydroxide, we should know that is a strong base. From theory, it's a group 1 metal hydroxide. And they react according to that equation over there. It is balanced. And they say 5.1, we have to classify the acid in terms of the specific number of protons donated. So yes, we know this is a polyprotic acid, okay? It can donate several hydrogens, right? Several protons. But in this case, because it has 3 hydrogens, it can donate 3, okay? So it is triprotic, okay? So for example, polyprotic, obviously from mathematics we have polynomials, and if we have 3 terms, it's a trinomial. So it's very much the same thing. So we have something that's polyprotic, but if it can donate 3 protons, it's triprotic. All right, so that's what we have over there. Question 5.2, so we got to consider this ionization reaction. Okay, ionization reaction over here. So we're creating ions, as you can see. And it's this reaction of the weak acid with water. Okay, so we have ionization going on. So 2 Ka values are shown. Circle the value that is the most likely for this acid. So this acid is a weak acid. So we know its Ka will be low. All right, so it will be this one. Okay, because this is a low Ka value. Okay, so I know the 7.1 is obviously more than the 6.5, but this is times 10 to the -4, and this is times 10 to the +2. Okay, so this number here that I've circled, I'll circle again now in red, this number is smaller. Okay, so that means that this is not very favored. The forward is not very favored. Okay, so that means we are not going to be getting very many hydronium ions. Okay, so that means our pH is going to be relatively high. Our pH will be high, so it will be towards 7 and not towards 0. Okay, it's not going to be very low. Okay, because we're not going to have a high concentration of these hydronium ions. Okay, that might come up, but it's important we realize that as well, just from theory. Okay, they say that that ion over there is amphoteric. Okay, so that means it can act as an acid or a base. All right, we should know that from theory. All right, so it's a circle the correct option between the brackets. In the ionization reaction shown above, H2A- is acting as an acid or base. So let's go back to our reaction. Here we have this H2A-, and what you'll see here, we need to be looking now at the reverse reaction. Okay, so we need to be looking at going this way. So we have H2A-, all right, and then its conjugate is this over here. Okay, so that's the conjugate, and here's a conjugate for water, or well, this hydronium that becomes water. So we need to be thinking, okay, what is this? Is this a base or acid? We know here is its conjugate. Okay, what happened here with its conjugate? Its conjugate has gained hydrogen, right? So what does it gain? It's gained a proton. Okay, well, we know the thing that gains a proton is a base. So this is a base, and then this will be the conjugate acid. Okay, so yeah, it's acting as a base. So that's what we're going to circle over there. It's acting as a base because it gains a proton or accepts protons. Okay, so from that, I believe the correct wording from that Lowry-Bronsted, whatever that definition, yeah, Lowry-Bronsted, it accepts protons. A base is something that accepts, and you can see over here, this is accepting. So it's acting as a base, whereas here the hydronium is actually donating. It's giving up a proton. So that's an acid. Okay. So they say write down an equation for the hydrolysis reaction of H2A- when it acts as an acid. Okay, remember hydrolysis is a reaction with water. Okay. So we have H2A-. We don't have to show state symbols because they have not asked for it. Okay, so don't include it. We could say aqueous, but they don't say it, so why include it, right? They don't ask for it, so why include it? Okay, let's not open up room for errors. Okay, but anyways, we know we're reacting with water. Okay, and this is a weak acid, so it's going to be a two-way reaction over here, and it's acting as an acid. So when something acts as an acid, right, so remember an acid donates protons. Okay, so what happens is it's going to be very similar to this reaction up here. Okay, it's going to be very similar, whereas you see how here we had H3A and then over here H2A, because it has donated a proton. Okay, that proton went over here. But the main point is it went from 3 to 2. So what's going to happen here? It's going to go from 2 to 1. So now it's just going to be HA, but now very careful, it's 2-. Okay, because we're losing a proton, so our charge is becoming more negative. Okay, and then what happens is this, so we're donating a proton, so then this becomes hydronium over there. So this is our reaction. Okay, this is a hydrolysis reaction over there. I just need to see if we need to balance this. So no, okay. So this is what would happen over here. I'm pretty sure it's balanced already, but they didn't even ask for it to be balanced, so there's no problems over there. So that's our hydrolysis reaction. Okay. Then they now say 5.3. So this salt dissociates completely in water. Define dissociation. Well, here it's just a splitting of ionic compound into its ions. Okay, so this will go into Na plus, and then obviously this has to be a 3 minus. Okay, because if there's 3 positive charges and the whole molecule is neutral, then we know this has to be minus 3. Okay, that might come up over here, and it is coming up. Okay, it is indeed coming up over here. So we have to complete and balance, all right? So very important, this one needs to be balanced. The equation for the dissociation of the sodium A compound in water. Okay, so again, don't be looking for this in your periodic table. It is not there, it's a hypothetical. So over here, we know we're gonna have Na plus. Okay, again, we don't have to show state symbols because they haven't asked, okay? But we know there's 3 of them. Okay, because of that 3 over there. Then what we do is we say plus A. And very important, we need to know what this charge is over here. But if we look on the left, I discussed this a bit earlier on the previous slide, we know the charge here on the left is 0. The whole molecule is neutral. So here on the left, how many charges do we have here? Or how much charge do we have here, right? We have 3, okay, times positive 1. So from here, that gives us positive 3. So, but we need this to then be something plus x is equal to 0. Okay, so we see that x has to be negative 3. So that's how I knew this is to the power of negative 3. Okay, sorry, 3 minus. We normally write it as 3 minus. Let me fix that. Okay, so that is the dissociation reaction, and it is balanced. Okay, there's 1 molecule of A here and 1 molecule of A here. Okay, you don't even have to put that 1 over there. Okay, so I hope that's clear. My handwriting is very shaky today for some reason, but I hope you guys can see. My handwriting at best is pretty not the best. But anyways, so we have to circle and say, is the salt acidic or basic? All right, where did the salt come from? It came from the reaction of, if we have to go all the way up, where did the salt come from? Here, this is where the salt came from. Okay, so it came from this reaction. So here we have an acid, a base, and this gives us salt and water. So this is where our salt came about. This is a weak acid, and this is a strong base. So weak acid plus strong base, we spoke about this earlier. So, sorry, I meant to write weak acid. So we spoke about this earlier in the paper. A weak acid plus a strong base, well, that's going to give us a basic salt. Okay, that means we're going to have a basic salt. All right, our solution will be basic. Okay, and that's got to do with which ions will undergo hydrolysis reactions. That's important to know here, but it's kind of just like, well, this is a strong base and it kind of like outmuscles the weak acid, so we're going to end up basic. So that's just a bit of theory over there. So we've got to go down, and this is a basic salt. All right, now we have this 5.4. So grade 12 learners were required to standardize a solution, standardize a sodium hydroxide solution by titration. Okay, so we're doing titration. So whenever we're doing titration, we got to know the process. You basically work out moles of one thing, do a mole ratio, work out the moles of the other thing, and then convert that to a volume. That's normally what we're doing. Okay, in this case, looks like we're going to a mass in the question. All right. Anyway, so it's important we have an overview of the problem before we jump into it. Okay, this is just, should be standard procedure if you've done enough practice. Okay, so let's have a look. So Zandi prepared a standard solution of that. Here's our concentration. Okay, very important. Let's put a C up there so we know. And this is in 200 centimeter cube volumetric flask. This problems because we need that. Okay. So we're going to have to divide this by 1,000. Okay, don't forget that. Very important. If you need to put a little star here, circle it. Don't lose marks because you're missing things like that. Okay. So she says, after filling the flask to the mark on the neck, she put a stopper on and mixed the solution well to ensure it was homogeneous. Okay. Calculate the mass of those crystals, and they give the molar mass that Zandi used. Obviously, they have to give us the molar mass because A, we don't know what A is. So we couldn't find their molar mass on the periodic table. Okay, but anyways, to calculate the mass, we know the concentration and we know the volume. So we can work out the number of moles. So I'm going to do that. C equals N over V. Okay, so my concentration is 3,81 times 10 to the negative 2 That's equal to my number of moles over my volume, very important, divide by 1,000. Okay, so when I solve for this, I get that my number of moles is 0.2 times 3.81 times -2. So I get 7,62 times 10 to the -3 mole. Okay, but they don't want mole, they want mass. They want mass. So we're gonna have to do moles is mass over molar mass. All right, we have the number of moles, 7.62 times 10 minus 3, and that's equal to, well, we're trying to find the mass, and the molar mass is 192. Okay, so I should be using a different blue. Okay, this blue is better. Okay, sorry about that. This is very light. All right, anyways, so now we got the right blue. Now let's get the right green. So that means that mass is, we just take our previous answer times by 192. So we're going to round to 2 decimal places. The mass is 1.46 grams. Okay, and that's for 4 marks over there. You could have done this in 1 step. I prefer doing breaking it down into 2 steps like this. All right. And then 5.5, why is it especially important that the standard solution be homogeneous when doing titrations? Okay, so what you want to do is, you prepared this. So obviously you want it to be, well, we'll get from the memo. All right, so firstly they use this aliquot, don't worry about that word. So all amount, right, every amount that you're putting into, that you're using this titration must have the same concentration. Okay, and here are the reasons. So our results are correct, precise, accurate. All right, over there, here's another thing, and or I prefer, so I would probably say it needs to be that, because everything needs to have the same concentration. I would probably say this, this first part over here. Okay, or even this one, concentration must be correct so the titration readings are precise. I'd probably use the second one here. Okay, what's very interesting is you can literally just say, or to get an accurate result. For 2 marks, you could just say that, to get an accurate result, which is pretty simple. I know a lot of people overthink these questions, but yeah, you could just say to get an accurate result. For me, I would just say, well, you have to have the correct concentration so that your titration readings are precise. Okay, so now we're doing a titration. So earlier I said we're dealing with the titration standard process, but this was not a titration. Okay, this was just a normal mole question. Now we're going into titration. Maybe we're actually going to have to do a proper one, but anyways, let's have a look. So now she pipetted that volume. So again, we're going to have to divide by 1,000 of that sodium hydroxide into a conical flask. Okay, so here we have our sodium hydroxide, and now she adds a few drops of indicator solution. There's the indicator, and titrated with the standard H3A solution. So she repeated this procedure several times and obtained an average titration volume of this. All right, so this is very important. We're going to be using this in our titration equations. Okay, so you see here we have a volume for this H3A, and we also have its concentration from here. Here's a concentration of what? Of this. Okay, so we're going to have a volume and a concentration. We can put that into moles. Then we're going to use a mole ratio, and then we're going to work out moles of sodium hydroxide, and then we're going to work out concentration from that. Okay, that's the process for titration, guys. That's the process you'll see in question 5.7. That's going to be our titration. But before we get there, she says, well, they say which one of these indicators would be suitable for her to use in this titration. So we need to think this is still a weak acid plus a strong base. And earlier we circled that our solution, our resulting solution slash salt, is going to be basic. Okay, it's going to be basic, and quite basic, right? Because it's for example, so we know it has to be basic. So these indicators here are for acidic pHs, right? pH below 7. But we know our resulting salt is going to be basic. So we can't be using these indicators that are only going to change color in acidic mediums, okay? We either need to use bromothol blue or phenolphthalein, right? So bromothol blue is also kind of acidic and slightly just over neutral. But we know we're going to actually be relatively basic, okay? Because it was a strong base and a weak acid. So we're going to be quite basic. Okay, so we're going to have to then use phenolphthalein as our indicator. So I'm not going to write that, but you would just put that there. Okay, which indicator? So it would be this phenolphthalein. And then they say state the color change that would be observed at the end point in this particular titration. Okay, so we need to think, what did we start with? All right, so we start with the sodium hydroxide. Okay, we start with this over here. And what we do is we turn this pipette, we turn this little wheel over here, and then that allows more of this volume to go through. All right, it allows now our acid to go through. So we start with a base in our solution, right? So this thing is basic, and what happens is we're dripping this acid in, so it's pushing it to the left, it's pushing it towards acidic, but not very acidic because it's a weak acid. So we know we're starting basic, okay? We're starting basic, right? So remember, pHs are 14 are basic. So we're starting basic and we're moving this way towards, we're dropping our pH. So the color change that's going to happen is it's going to be pink to colorless, okay? Pink to colorless. Okay, those should be relatively easy marks over there. Okay, now in 5.7 is what I've been talking about this whole time, this standard titration process, okay? They want the concentration of sodium hydroxide. It's unknown. This is an unknown concentration. This is a known concentration. That's why, so it's the known concentration, okay? And that's why it's the standard solution. Okay, standard solution. Oh, standard volume, standard solution, okay? So it's just this process, guys. We use volume and concentration to find the moles of the known thing. Then we do a mole ratio to find the moles and concentration, well, the moles and then the concentration of this thing, okay? Because if you look, we know the volume of, this is a volume for sodium hydroxide. Okay, so I've given a broad overview, but we're going to go into this now. All right, so we're working with H3A. All right, I like to label. I do recommend labeling. All right, so we're working with this. We know that concentration is number of moles over volume. Okay, we have to find the number of moles because we're going to be doing a mole ratio. Okay, so continuing with this, we know its concentration. Where did they give the concentration? It was a bit quite higher up. So it's this 381 times 10 to the negative 2. Okay, 3.81. What's actually interesting is I did work out the, I think I already worked out the number of moles, but I'll do it again. Why not? Oh yes, I worked out the number of moles, but that was for a different volume. Okay, so don't, all right, I need to confuse myself here. So my main point was this. I already did, I worked out the number of moles, but that was for this volume. Okay, this was for a volume of 200 centimeter cubed. But I no longer have that because I used, sorry, we're jumping all over here. I used over here, a lot of circling, very messy. I've used this volume. Okay, this is now my new volume of H3A. So do not use that 200. We're using this 32.6. Okay, but again, we have to divide by 1,000. Okay, so it's this 32.6 and divide by 1,000. Okay, so I like to just put that in a bracket, divide by 1,000. Okay, and then n is over that whole thing. Okay, so when I solve for n, I'm going to be getting 3.81 times 10 to minus 2 times by 32.6 divided by 1,000, all in a bracket. Okay, and if I do that, I get this for my number of moles, 1,242 24206. Okay, so I know there's 5 decimal places there, but I want to use the whole answer. It's really so remember, during the calculations I want to work 4, but my final answer wants to be 2. Okay, but that's close enough to 4 that I'm going to write down all of that. All right, now I have to do a mole ratio between my known, okay, my standard solution, and what I'm trying to find out the concentration of. Okay, so I write down my basic mole ratio, which is 1 to 3, but what I actually have is 1,24206 times 10 to the minus 3 moles of that. So then to just get the moles of the sodium hydroxide, I just take my previous answer, times it by 3, and I'll get this 3,72618 times 10 to the minus 3. So now I have moles, but let's not forget, what were they asking for? They want the concentration of sodium hydroxide. I have the moles, this is my number of moles, and I also have my volume. Okay, this is my volume here of sodium hydroxide, 25 centimeter cubed. Okay, so I have C is N over V, and that's the 3,72618 times 10 to the minus 3. That's over my volume, which is 0.025. I decided to just divide instead of doing this time. But anyways, we take that previous answer that should be on your calculator and divide by that, and we get a concentration, careful, to 2 decimal places now, of 0.15, and the units mole per decimeter cubed. Okay, so that is not correct. Okay, so not 2 decimal places, and yes, the front instruction does say 2 decimal places, but here they want to 3 decimal places. Okay, so this one's actually 0.149. Okay, so you would lose a mark if you don't put it to 3 decimal places. Okay, so this is literally just a standard way to do titration. Okay, it's literally just a standard process. We work out the number of moles, mole ratio, work out concentration. Okay, so these titration questions shouldn't be too complicated once you practice them enough. Okay, I guess everything's complicated, but with enough practice it becomes easier. All right, so now we have Mikey's also using 200 centimeter cubed a volumetric flask to make a standard solution. So he recorded the mass of these crystals, dissolved the crystals, then added more distilled water. He carefully removed some of the solution. That's a bit of a whoopsie. Okay, he's removed some of the solution. Okay, but the problem with removing some of the solution, these crystals are dissolved, right? So he's actually removing some of this H3A. So that means his number of moles are going to go down. Okay, which is problematic. That's a bit of a whoopsie. So he's done that until the bottom of the meniscus was on the mark. Okay, so the bottom meniscus stuff is right. He then placed a stopper and mixed the solution well. Okay, we want it homogeneous, that's normal. He calculated the concentration of the solution now using the recorded mass and volume. Okay, but the problem is he actually has less than this recorded mass. Okay, because he took some of it out when he removed some of the solution. Okay, because over here these crystals are dissolved, right? So we have all these different ions in here. But what he did is he took this dropper, right, and he took some of them out. So some of these crystals would have left. Okay, so that means the mass would have decreased, which means the moles would have decreased. Okay, so what happened here, we have to circle the correct option between the brackets and explain your answer. Okay, so the actual concentration is going to be greater than, less than, or equal to the calculated value. Well, the actual, okay, so concentration is number of moles over volume. Okay, because he's removed mass, he's removed the number of moles. Sorry, decreased the number of moles. He's removed some moles. Okay, so if concentration is directly proportional to number of moles, so if you decrease the number of moles, you're going to decrease the concentration. So his concentration here in 5.8 is going to be less than, okay, and the reason is he's removed some of those crystals, right? He's removed Here the memo says he's removed some of the dissolved solute. Okay, so we can literally just say he removed H3A. He removed some of this dissolved solute, so we'll just say removed dissolved solute with that drop, some of the dissolved solute. Okay, so that's what we have in 5.8. 5.9, they say we now need to consider his calculated sodium hydroxide concentration after each titration. Circle the correct option between the brackets. Mike's calculated, all right, so the calculated sodium hydroxide concentration would be equal to, higher than, or lower than the actual value. Okay, so the thing is, we know when we do a mole ratio, okay, is going to be between the H3A and the NaOH. Okay. So what's going to happen is, if we use these actual values, right, the actual moles should be less. So that means that actual moles of this sodium hydroxide will be less. And again, if we do concentration over volume, the actual concentration, right, because the moles, number of moles is proportional to concentration, the concentration actually of the sodium hydroxide should be less. Okay, but his calculated NaOH is actually going to be higher than that. Okay, because he's going to be using these theoretical values, okay, instead of what he actually had. His actual is going to be less than his calculated, because his calculated is going to be using a higher mole value than what he actually had. I thought we'd make a table. Okay, so let's recap. So what happened here with Mike is, because of what he did here, and he removed some of his dissolved mixture over here, because he removed some of it, he actually, in terms of your actual, he has less moles than what you would expect, right? Because he has less of these crystals, right? Was it crystal? Yeah, so it was some of these crystals. So because he has less of these crystals, right, and he's actual, because he took out some of these crystals, he's going to have less moles, and because of that, he's going to have, his concentration is going to be less, right? Because concentration is directly proportional to number of moles, right? So I thought I'd include that in the table. Okay, so when we look at what he calculates, what he calculates, he's not taking into account that he actually has less. So all of these calculations are going to be more. Okay, so he's going to calculate more. So what's important here, this is for each H3 crystals, right? So this is for his aqueous solution of his acid. So over here, the actual concentration of this solution is, over there we said it's going to be less than the actual, all right, concentration is going to be less than the calculated. All right, so but now what they're asking, they're not asking any longer for the H3A, they're asking now for the sodium hydroxide, and we need to determine, is it equal to, higher than, lower than the actual value. Okay, so this one's a bit interesting because here we did the table for H3A. Okay, so but we know if we do a mole ratio between H3A, where's our, we know it's 1 to 3. Okay, it's not important the actual values, but I'll include it here for completion's sake, I suppose. But anyways, we know our actual constant ratio here is 1 to 3. Okay, we're from our mole ratio. So we need to think, if in actual, because he's going to have less moles of this, he's going to have less moles of that because of the mole ratio, right? So that's the connection, because now they're asking for sodium hydroxide. Okay, so we kind of need to think about this mole ratio to determine the connection. Okay, so the mole ratio gives us that connection. Again, the numbers aren't important here. It's more the connection between, if we have less H3A, we're going to have less of this. Okay, so they say here, circle the correct option between the brackets. Mike's calculated NaOH concentration, he's calculated, and we need to compare it to the actual value. Okay, so what happens here, because his moles, right? If we do this table now, right? If we do a table for NaOH, that table will be identical to this table. Okay, it will be identical because we're also going to have less moles of this because we have less moles of this H3A. So that means his actual concentration, so this table is identical, okay, for NaOH. So I want you to start thinking about this table for NaOH. All right, a lot of thinking for 1 mark. Okay, there's easier ways to think about it, but this is the best way for me to explain. Okay, so maybe take some time to think about this for yourself. Okay, it might be easier and quicker. But anyways, so a lot of things. We have to think about this table now in terms of sodium hydroxide. So they're asking about his calculated compared to the actual. Well, we know his calculated concentration is going to be more than, okay, it's going to be more than, higher than, okay, the actual value. So that's the answer here. And then the reason here, there's a few things you can say, but the titration volume is going to be higher. All right, his actual titration volume is going to be higher. So that's one thing. So I'll show you. So yeah, this is the explanation from the memo. I did not take this explanation. What I did is I used this mole ratio. Okay, so personally, so this is what the memo says, the titration volume will be higher. So very interesting, they used this and they said the volume would be higher, so that means the concentration would be less. So my argument here is we're going to actually need fewer moles in reality than we would need. Okay, so my arguments between here are mole and concentration, because we're going to need fewer moles of sodium hydroxide. Okay, our concentration will be less than, our actual concentration is going to be less than the calculated, so then vice versa, the calculated will be more than the actual concentration. Question 6, Sam wrote the following cell notation to represent a galvanic cell. So we have to complete the above cell notation, so we need to complete it on here, and we have to include one important component that Sam left out. They also tell us that standard conditions were not required. Okay, so what we should realize is, because we have, this is a gaseous electrode. This is a gaseous electrode. Because we have this gaseous electrode, we need to be having an inert electrode. Okay, so what we're going to be using is we need platinum. Okay, so we're going to need platinum. Okay, and what's important is we have to, that's an S by the way, to show that it's solid, and we have to put a line here because remember we use a single line whenever there's a change in phase. Okay, because we went from aqueous to solid, we have to put this line over here. Okay, so because again we have a gaseous electrode, we have to use we can't do that. We have to use a inert electrode in its place. Okay, so that's just from theory. We have to define anode. Well, over here the O kind of gives it away, and you'll see what I mean. It is the electrode where O, oxidation, takes place. Quite an easy definition. Okay, and identify the anode in the cell. Okay, so when we write it in cell notation over here, it is it's in alphabetical order. So the anode will be on this side and the cathode will be on this side. So it's alphabetical order. Okay, so the anode is this, iron. Okay, so you can say Fe or you could say iron. Okay, or Fe over there. So yeah, it's in this order. Anode will be on the left, cathode will be on the right. But you can also realize that iron becomes iron 3+. And to do that, this is a oxidation reaction. So this is an oxidation reaction. We know oxidation takes place at the anode. Okay, it's oxidation, the electrons are on the right. And remember, you can use oil rig to remember that oxidation is a loss of electrons. So iron has lost electrons. The electrons are on the right hand side of the equation. All right. Over here they say write down the net ionic equation for this reaction that takes, for the reaction that takes place when the cell operates. All right, what I like to do is I like to write out my half reactions, my anode half reaction, my cathode half reaction. Okay, so my cathode half reaction, what's happening in my cathode is it's a gain in electrons. Okay, so it's happening this way. All right, so chlorine gains electrons, right, because reduction is a gain, So it gains electrons, it has to gain 2 electrons, okay? And then that becomes 2Cl minus, all right? So you don't really have to think about these because this is on our reduction table. This is on our electrode reduction table. Let me actually bring that up. So we didn't actually have to think about this balancing over here, right? Because we're looking for chlorine, okay? And we know chlorine is reduced, okay? Because reduction happens at the cathode, all right? It's reduced. So we're looking for chlorine somewhere here on our table. And remember these reduction, this is, the order is reduction, and then, so my main point is, let me not do that. So remember, these are all written as reductions, right? Because you can see all of these have electrons on the left-hand side. So these are all a reduction reaction. So here we're looking for chlorine, this Cl2 on the left-hand side, right? Because this is a reduction reaction. This is a reduction because reduction is gain. So that's from rig, gain of electrons. Okay, so we're looking for Cl2 somewhere over here. I might have missed it already, but Cl2, where are you hiding? Cl2, where is it? Should be somewhere down here. Here it is. Okay, perfect. So here it is. We didn't have to think about the balancing because we can just find it in our table. Okay, the other one is a bit of an interesting one because it was iron being oxidized like this. Okay, this should be a 3E. So we also didn't have to think about this one. Okay, let me just write, this happens at the anode. So let me rather write oxidation. Okay, oxidation. So because remember, all of these are written as reduction reactions, we actually have to look, so left to right is reduction. We have to look for iron on the right-hand side. Okay, because right to left, if left to right is reduction, right to left will be oxidation. Okay, so we're looking for iron. Okay, here's iron, but the problem is it becomes Fe2+. That is not what we have. Okay, so don't look at that one, it's not this one. So we keep looking, here's iron, and this is exactly what we need. Iron goes to that. Okay, but we read this right to left because that's what we have here. Oxidation is a loss of electrons. Okay, remember oxidation reactions, electrons will be on the right. All right, so my main point for this is we can use the table to write these two half reactions. Okay, so remember this is, I'm not going to write the full, this is the oxidation half reaction and this is the reduction half reaction. Okay, but the main point here is we're going to need these to write the net ionic equation. Okay, but we have some issues because electrons are not balanced. We need to be balancing electrons. Okay, so here's 3 electrons. Okay, let me neaten this up a bit. So we need to be having the same amount of electrons on the left-hand side as the right-hand side. So currently we have 2 on the left and 3 on the right. So we have to multiply, we essentially need to find an LCD, right? The lowest, well, LCM, lowest common multiple, but it's the same idea as LCD. So what you'll see is I have to times this line by 2 and this line by 3. So I can get 6 electrons on the left and 6 on the right. All right, so I'm just going to write that up here then. Okay, so we will have this. I forgot to put a 2 in front there, plus 6 electrons. So you'll see our electrons are sorted there. And then below that we'll have 3Cl2 plus 6 electrons. And then that is going to go to 6Cl minus. Okay. So at this point, what we can do is we can cross out our electrons because they're on both sides of our equation. Okay. And what we can do now, our net ionic equation is everything on the left. Okay. So 2 Fe plus 3 Cl2. All right, so you see how here we have, here's our arrow and this is to the left of the arrow, and here's our arrow and this is to the left of the arrow. That's why I put them on this side. All right, and now obviously if those were on the left of the arrow, I'm going to be showing what was on the right of the arrow. Let me just move this across, and what we had on the right hand side of the arrow is 2 Fe3 plus 6Cl minus. Okay, so I spent a lot of time on this, but this is essentially the net ionic equation. Next up, we just have a definition, standard process. Well, I guess I should read over here. So for the cell to operate at standard conditions, standard solutions of those ions and those ions need to be prepared. So to find standard solution, well, here we go. It's just a solution of known concentration. Perfect. Don't lose those 2 marks. They then say the standard solutions are prepared using the ionic salts, iron nitrate and calcium chloride. What should the concentration of these solutions be? Okay, so obviously if there's for 3 marks and you think, oh no, a lot of people just think, oh no, it's just 1 mole per decimeter cubed, right? But that's what they need to be, okay, of these ions. Okay, so they told us about these ions, so we need these ions. Okay, in standard conditions we need 1 mole of this, 1 mole per decimeter cubed of that and that. Okay, but we need to be careful because we actually need to look at these dissociation reactions, right? So what happens is this is going to dissociate to, I'm just writing it here, it's not the answer, 3 plus 3 nitrates. Okay, that's the dissociation reaction there. Okay, so 1 mole of this creates 1 mole of that. Okay, but look what happens now, because calcium does that, but now we have 2 moles of chloride ions rather. Okay, so 1 mole of this creates 2 moles of this. Okay, so we need to be thinking about that. Okay, and obviously some, maybe not alarm bells, but we should have been a bit suspicious that this was for 3 marks if we're just going to write 1 mole per decimeter cube, 1 mole per decimeter cube. So this was fine, right? Because 1 mole creates 1 mole. Okay, but the problem was with this 1 mole of this salt, right, created 2 moles per decimeter cubed of, well, technically 2 moles, but also in terms of concentration, but it made 2 moles of that. So what we need to do is they're asking what should the concentration of this be? So it needs to be a half, right? It needs to be a half so we can get 1 mole on the other side. Okay, because of that mole ratio situation. Okay, so but we also do need those units. Okay, so don't forget the units. All right, you would lose a mark for the units if you don't include them. Okay. Here we have, so Sam says, for the cell to be operating at standard conditions, the atmospheric pressure needs to be that amount over there. But we don't really care about the atmospheric pressure. The only thing that matters is we care about our, if we have any gaseous compounds, sorry, not even if we have any gaseous substances, right? For example, here we have chlorine gas, that needs to be at that pressure. Okay, so that needs to be at this 1,01 times 10 to the 5 Pascal. So it's not atmospheric pressure must be that, it's the pressure of the chlorine gas. Okay, so we can just say that the pressure of chlorine gas, right? Because we don't really care about the atmospheric, we just care about our substances. So the pressure of the chlorine gas must be that value over there, 1,01 times 10 to the 5 kPa. I wanted to say kPa, but it's just Pascal. Okay. Obviously, if you just shift that to 101, then you get to kPa, but don't worry about that. So yeah, it's just the pressure of chlorine gas needs to be that. Now they say calculate the standard cell potential E cell for the cell. Okay, so we're gonna have to use our formula sheet. Here we have 2 formulas we can use for E cell. I much prefer this one here at the top. So that is exactly what I'm going to be using, right? I'm going to be saying E cell is equal to this, basically just rewriting the formula. All right, and so we have that down for us. Well, now we need to find out what our cathode was, but we wrote that all the way at the top. We've been dealing with it. So the cathode was this side. Okay, the cathode, remember alphabetical order for galvanic. The cathode was this. So what happened at our cathode was this reaction here. okay, because that's our reduction half reaction. So we just need to look for this reaction and write down the number we see, okay, on our standard reduction potential table. So here, okay. So remember, we're looking for the Cl, so Cl2 going down. So we're looking for this one basically. Okay, and it's pretty simple. We just write this value here. Okay, so that becomes 1,36. Okay, and then we open up a bracket, and what happened at our anode, it was iron going to this ion over here, ion. Okay, so we have that. So now what we need to do, we just need to look at our reduction table again and just find that thing. Okay, so again, we're looking where iron is oxidized to become this. Okay, but we need to be a bit careful. So firstly, we need to keep an eye out, because this was Fe2 plus, what we discussed earlier, and this is Fe3 plus. Okay, so this is the one we want. Okay, but remember, it's an oxidation reaction, so we actually, we would read it right to left, but don't change this value. Okay, don't change it to a positive. The way the formula works is it sorts that out for us. Okay, so this was the right reaction. Okay, this was the right place, so we just put this value. Okay, so you'll see how it will work out, because now it's that negative 0.04. Okay, so yes, don't change that to a positive just because we're reading it. So just because we're reading it right to left, don't change it to a positive. Okay, the formula sorts it out for us. Okay, we just need to identify where in the table. Pretty easy, right? And then this is also pretty easy. We just put those numbers together. You can use a calculator. You shouldn't really need one for this, but if you want to, feel free. And we just need to remember the units for this is volts. Okay, so, and that's for 4 marks. All right, they got a lot going on over here. Okay, 4 marks. So they say Sam now adds some silver nitrate solution to the chlorine half cell, causing solid silver chloride to precipitate. How will this affect the voltage of the cell? Circle the correct option over there, and we also need to say because. Okay, so you're gonna have to give a reason. Okay, so explain your answer is what we're gonna have to do. Okay, so that is question 7. That's not what I wanted. So if we have a look, so let's draw this chlorine half cell. Okay, so obviously we will have our platinum electrode, and we'll have like some like gas tube over here, so the chlorine gas can flow around there and do its thing, and we will have, this will be in solution. Okay, so remember, in solution we will have chlorine ions. We will also have calcium ions, remember, because we use that calcium chloride, but we don't really have to think about that. What's important here, we need to be thinking about chloride ions. Okay, and we need to be thinking of what's happening with that. Okay, so what happens is, as this reaction takes place, remember, chlorine half cell was it was a reduction half reaction, right? Because we had chlorine going to this plus 2 electrons. There should be a 2 here. Okay, so we have this reaction. Okay, so what happens is, this is the reaction that's happening. Okay, so what we know is the concentration of these keeps increasing. We keep getting, right, so we have chlorine gas over here, Cl2, and what happens is that just keeps putting into solution more chloride ions, right? Each time that this chlorine atom, this chlorine molecule is, sorry, I actually wrote the reaction wrong. This is what's happened. So chlorine gas is actually not oxidized, as I just said. It is reduced. So this is what we had. Okay, this is what we had before. I'll show you over here. Okay, I just wrote it wrong. I wrote it as a oxidation. Well, I wrote it weird. It was just wrong. Okay, but anyways, this is what we have. So, but the point still stands. As we go, we're creating more and more of these. Okay, as chlorine gas is reduced. Okay, gain an electron reduced. So yeah, my main point here is we keep just adding these chloride ions, right? We keep, each time this chlorine gas is reduced, we keep getting more and more chloride ions, which is a problem. Okay, because the charge that's developing here is more and more negative. Okay, so it's kind of like, imagine you have a really packed, relatively packed room, and what happens is you just keep opening the door and letting more and more people. It gets a bit packed, right? and that's not very good. You're going to struggle to put more people into the room. Okay, so what happens then is that's problematic. Okay, but what we do if we add the silver nitrate, okay, we can actually get solid silver chloride. So what that means is we have some silver ions in here. Okay, so my diagram's getting a bit cramped. Okay, but anyways, we're gonna have silver ions in here, right? We're gonna have Ag plus. Obviously this is out of solution, but yeah, just imagine here, Ag plus. Okay, and what happens is these are actually going to pair up. Okay, silver is going to pair up with chloride, and it's going to cause solid silver chloride to precipitate, right? So what that means is we're getting rid of these chloride ions. Okay, so it's actually people are leaving the room. Okay, it's making it easier for us to fill up the room. Okay, so what that means is the voltage now is actually going to increase. Okay, the voltage of the cell will increase, and it's easier, right? So obviously we're going to be careful with our wording, but the main idea is it's just easier to we're getting rid of those chloride ions. Okay, so what we're going to say is we're going to talk in chemistry now, so we're going to be saying that the chloride concentration decreases. Chloride concentration will decrease. Okay, and we know it's decreasing because it's pairing up with that silver to form a precipitate. Okay, so the chloride concentration decreases. Okay, so what's very important is we also need to be saying that the forward cell reaction is favored, and the reason is to counteract the stress. Okay, so this is a bit of a Le Chatelier problem. Okay, so again, you can kind of memorize these bullet points. Counteract the stress. All right, but you might be thinking the forward reaction, it comes from this, right? Or you could look at our net ionic equation. I mean, it's pretty much the same thing. So what happens is if this concentration decreases, we know from Le Chatelier we're going to be trying to make more of those. Okay, so forward is going to be favored, and then that means we're going to counteract that stress. But if the forward is favored, that means the voltage is going to increase. Okay, and vice versa. So have a look in your textbook or some other past papers and see if there's questions like this, because it's good to practice these questions. Okay, let's have a look what's cracking in question 7. So in both cells, a concentrated aqueous solution of copper 2 sulfate is electrolyzed using pure electrodes. All right, so we have cell A on the left and cell B on the right. So both of them have these copper sulfate, this solution. So that means we're going to be having copper 2+ ions in here and here. Okay, so nothing different there in the solution, right? But what is different is here we have solid copper as an electrode, and here we have graphite. So remember, graphite is just carbon. Okay, it's literally just carbon, and it's an inert electrode, so it's not going to be it's not going to be oxidized, it's not going to be reduced. Okay, so that's what's going on over there. So on the left we have solid copper. Let's just keep that in mind. And now they say in cell A copper electrodes are used. Okay, but we saw that. And now they say circle the correct answer between the brackets. At the cathode, that is going to be reduced. Okay, so let's have a look. So remember, reduction is a gain in electrons. Okay, so we're going to have to use our standard electrode potential table, and remember, if we read left to right, that is reduction. Okay, so left to right is reduction, left to right is reduction. You can maybe remember it like that. Left to right is reduction. Okay, so we are looking for the things that will be reduced. So we are looking where copper is gaining electrons, for example, if that is possible, or we're looking where copper ions are gaining electrons, however many, right? So even forget the twos, we're just looking for, or water, right, is gaining electrons. Okay, we're just looking for things to be reduced. All the sulfate ions, okay, are gaining electrons. Okay, so let's have a look. We're keeping our eye out for water, copper ions, and also for sulfate ions. Okay, so we're gonna go look left to right here. So left to right, nothing. Here's water. Okay, so this is a possibility. So we have water gaining electrons. Okay, that can happen. But have a look here. This is a negative value. So that's not very favorable. Okay, but we're going to keep that in mind. Let me not erase that actually. We're going to keep that in mind. Let's keep looking though. So we're looking for copper. Here's sulfur, but we have sulfate. Here's sulfate. Okay, so here we have sulfate, but also we need to be a bit careful because here are hydrogen ions. Okay, but let's include this anyways. Okay, so there's our sulfate. Okay, so now we're looking for solid copper or copper ions. Hopefully we'll see. Oh, and actually right below here we have copper ions. Okay, and if you look, there will not be solid copper here on the left. Okay, so essentially we have these things going for us here. Okay, and we need to look at this. We need to look at these values. Okay, so if these values are positive, that means that it is more likely to happen. Okay, so for example, fluorine over here very much wants to gain electrons, okay, to become ions, but we know that because fluorine's very reactive anyways, right? So the main idea is big positive number, okay, it wants to go this way, it wants to go left to right. Okay, if it's a negative number, big, it doesn't want to go this way. So for example, lithium ions do not want to gain electrons. Okay, but it very much wants to go the other way. Lithium wants to be oxidized, okay, because remember, if we go right to left, it's oxidized. Right to left is oxidized. So lithium wants to be oxidized. It actually wants to lose electrons, right? Because remember, oxidation, oil, lose. Okay, so and you see lithium is losing electrons. Okay, so it's important you understand the table like that, right? So you'll see here that these copper 2 ions are more likely than sulfate, okay, to gain electrons, to undergo reduction. So what happens is, so I've circled a lot here, so I just did that for illustration, but it's these ions that will be reduced from that table. Okay, now what we're doing is we're going to be looking at the same thing, but we need to see what will be oxidized. Okay, so now what we need to do is we need to look right to left. Okay, we need to look right to left, and we're looking for the same things. We're looking for water, we're looking for copper, copper ions, and sulfate ions. Okay, so we're looking right to left. So here's lithium, over here calcium, close, right? But we're looking for copper, C2. Here's H2, but it's not H2O. Keep looking, copper anywhere. Here's H2 again, not H2O, H2S, no. Here's SO2, careful. Okay, but so here's water, but SO2, we don't have that, right? So we can't do that one. Here's copper, perfect. Okay, here's copper, and if we keep looking, is there any water? Here's water. Okay, so we'll get back to that. Let me do that same thing before, but I'll just do it now in blue. So where did copper go? So here we have copper. Okay, and on this side here we have water over here, and any sulfate here. Also we have water again over here. Okay, so what we need to be looking now is, so there's two ways to look at it, well, multiple ways actually. So because we want to go right to left, okay, so for example, this is a very positive number, these are very positive. Okay, so again, that means we want to go left to right. Okay, so if things want to go left to right, very much so, will it want to go this way? Will water want to go this way? No, right? Okay, whereas copper, it doesn't really want to go left to right. Okay, it's more favorable than the other way. Okay, but because we're comparing with these other substances, copper's more, it's more happy essentially. It's happier to go, it's happier to undergo oxidation because this is a smaller positive. Okay, another way you can look at it is the thing that will be oxidized is a stronger reducing agent. Stronger reducing agent. Okay, so another way you can look at it, and it's probably the better way, to be honest. I prefer the other way, but anyways, we're looking here, so increasing strength. So I cut out this arrow, but it should be like that. Okay, so we're looking what is the stronger reducing agent between all of these things. Okay, so over here the bottom is low strength of reducing agent, at the top of very strong reducing agents. Okay, So here we had water. Okay, water over there. And there was another spot where water was here as well, right? But these are very weak. It doesn't have a very strong reducing ability, okay? Whereas copper is higher up here. So it's a stronger reducing agent than water is, okay? So therefore, if it's a stronger reducing agent, it will be oxidized, okay? So there we have that, okay? And you can also do the same situation for this first one, but reducing, now we're looking for the thing that is the stronger oxidizing agent, all right? And I'll show you how that is true as well for the previous question. Okay, let me just circle copper. Did I do that here? Yes, I did. Perfect. Okay. So let me just look at the other way. So over here, the thing that will be reduced is the thing that is a stronger oxidizing agent. Okay. So again, we're looking now on this side because here's the strength of oxidizing agents. Okay, so at the top here, not very strong oxidizing agents, but at the bottom, strong oxidizing agents. Okay. So let's just work from the bottom up, okay? So if we look here, it's H2O2, not what we have. Let's keep going. O2, remember we're looking for the water, copper, or sulfate. Okay, and over here you'll see we have this, and that is a stronger oxidizing agent, okay? Because remember the strong ones are down here. This shows increasing strength. So that means that copper 2+ ions are stronger oxidizing agents than the sulfate ions, just by a bit. But that means that copper 2+ ions will be reduced. Okay, perfect. Let's now continue. So I spent a lot of time on that, but I feel like it's an important area of emphasis. Okay. Let's now look at 711C. They say the concentration of the solution as time passes will increase, decrease, or remain constant. Okay, so we're looking at cell A. So what happens in cell A is, so this side, this will be our anode, and this will be our cathode, all right? Because this is positive and negative, okay? So we know that, so at the anode we have oxidation, okay? So we have oxidation, and that's a loss of electrons. So that means this copper is losing electrons to become Cu2+, okay? And on this side we have cathode, we have reduction, which is a gain in electrons. So in that case we have these copper 2+ ions gaining electrons to become solid copper, okay? So what we can deduce from that, the mass at the anode will decrease and the mass at the cathode will increase. But they're asking about concentration, okay? But what's happening is at the anode, one copper atom, okay, one copper atom becomes a copper 2+ ion, okay? And what happens at the cathode, one copper 2+ ion becomes solid copper, okay? So basically we're putting one ion in and using one ion, okay? So what effect is that going to have on our concentration? It's going to cause our concentration to remain constant, because we're not changing the number of moles of copper 2+ ions as things are being reduced and oxidized, okay? Because we're creating one, using one, creating one, using one. Okay, so I hope that's clear over there. Now we are in cell B. Graphite electrodes. Write the chemical symbol for graphite. So graphite is just carbon, okay? It's just graphite. No, well, it's just carbon, okay? And they say give a reason why graphite can function as an electrode by referring to the structure of graphite, okay? Well, don't let this throw you off, okay? Don't go into some hectic molecular analysis, right? Why do we use things as electrodes, right? Electrodes need to conduct electricity, okay? And the way they do that is they have delocalized electrons, okay? They have electrons that are free to move. So we can literally just say it has delocalized electrons, Simple as that, okay? So it's not a metal, but we don't have to go into the whole structure of graphite and how it can conduct electricity along the layers. We don't really care about that. It's like metals. Metals have a sea of delocalized electrons. That's why they conduct electricity. And because of the structure of graphite, they don't ask for the specific structure. It also has delocalized electrons. And we need those for flow of electricity. Okay, that's why we use electrodes. We need things to conduct electricity. Okay, so remember, keep it super simple. Let me write that. Keep it super simple. And now we're still looking at cell, so we're still looking at cell B. We're just now on part C. Okay, and they have this: circle the correct answer between the brackets. At the cathode, what is going to be reduced? Okay, so I'll show you with our, so obviously we're going to be using our standard electrode potential table again, but we know why we use graphite electrodes is because they're inert. Okay, so they're not going to be reduced and they're not going to be oxidized. So we can immediately cross out graphite over here. Okay, but what's important is okay, yeah, they're not going to, we can also confirm it with the table. You'll see carbon is not on the table, but we know they're inert. Okay, so we can even just ignore that graphite stuff over there. And yeah, you were a bit stuck if you didn't know what graphite was, like the symbol. It's just carbon. Okay, so we're going to be looking for carbon on our standard electrode potential table. Okay, so a better way is not looking at those negative and positive numbers. But anyway, so if something is going to be reduced, what does that mean? That means it's going to be this, out of these three, it's going to be the strongest oxidizing agent. Oxidizing, yo, I butchered that. Oxidizing. Oxidizing, here we go. Okay, this is why I don't make English videos. Okay, oxidizing agent. All right, so we're going to start where? So here at the bottom are the strongest. So we're going to start at the bottom and we're going to be looking for H2O, SO4, 2- and copper 2+. But now just copper 2+. You'll notice how there's no copper solid, right? There's no Cu, all right, like we had before. Okay, so we're looking here at the bottom, we're looking for H2O, or copper ions, or sulfate ions. Okay, we're looking, here's H2O. Okay, but the problem here with this H2O is it needs oxygen gas. Okay, it needs oxygen gas, and we don't have that. Okay, we don't have that, so we cannot use this. That one's not relevant because we don't have oxygen gas. Okay. So what happens here is you'll notice that copper 2+ is the first one we see. And again, it's slightly stronger than SO4, 2-, but that will then be reduced because it is the stronger oxidizing agent. Okay, so we're going to circle this again. All right. Now we need to think. So immediately now we pretty much know, well, we don't actually know that, but yeah, let's not actually do that. So now we're looking for the thing that will be oxidized. And again, between those three, we're looking for the thing that will be the strongest reducing agent. Okay, strongest reducing agent. All right, so the strongest reducing agents, remember I cut out this arrow by accident, but it looks like that. So the strongest reducing agents will be here at the top. So let's look from the top downwards. Okay, and again, we're looking for copper 2+, and we're looking for H2O or SO4, 2-. And at this point, I just want to point out how carbon is nowhere to be found on this standard electrode potential table. Nowhere to be found. Okay, so that's why we don't even bother with that. Okay, it's important you get comfortable with this thing. Make it be your friend. Okay, you don't want to be fighting with this thing in your exams. Okay, but anyways, the thing that is oxidized, strongest reducing agent. Let's look. Strongest reducing agents are where? Here at the top, right? The top of this arrow. Okay, so we're going to read this down and we're looking for those substances. Okay, copper 2+, H2O, where are you? Okay, we're close. This is SO2 though. Remember, we need this thing, but we need it on this side. So it's not there. Here we have copper. Okay, but careful, that is not one of our options. We're looking for Cu2+. So we cannot look at that one. Okay, so we keep going. H2O2, not what we're looking at for. We have H2O. Keep going, we keep going, and here we have this. Okay, and because we hit this first, that will, this is what will happen. This is, because this is the strongest reducing agent, because it's closest to the top, this is what's going to be oxidized. So in this case, water is going to be oxidized. All right. And what will happen is, remember oxidation, we read right to left. So what happens is we're actually going to be producing oxygen gas here. Okay. So yeah, that's how we do that. So yeah, I hope that kind of helps you make the table be your friend. Okay. Now they say the concentration of the solution as time passes will decrease, increase, decrease, or remain constant. Okay, so let's go up to the solution. Okay. So we know that if we recap, we know that copper 2+ are reduced. Okay, so copper 2+ ions gain electrons. Okay, so let's just identify. So here's positive, here's negative. So here we have the anode, here we have the cathode. Okay, so cathode is where reduction takes place, so that's a gain in electrons. Okay, so here we're going to have the copper 2+ ions gain electrons to become solid copper. Okay, that's what's going to happen there. And here at the anode, this is where oxidation takes place, and we discovered that's where water, okay, water is going to do its thing, and it's going to lose electrons and then become that oxygen gas. Okay, but the main idea here is we're looking at concentration. Okay, and the issue is we are losing copper 2+ ions and we are not gaining them back like before. Okay, so what's happening we're reducing the number of moles of copper 2+ ions. So what happens here, the concentration of the solution is going to decrease as time goes on. Okay, that would be our answer over there. And now in 7.2, you are required to plate a lead rod with nickel. You're supplied a cell, a beaker, an ammeter connecting wires, and these things. A lead rod, a nickel rod, an aqueous solution of lead 2 nitrate, aqueous solution of nickel 2 nitrate. So give the formula of lead 2 nitrate. So lead we have to know is Pb. Okay, nitrate we need to know its valency. Well, we know the valency of lead. So technically you could do one of these cross things where that's a valency of 2 and 2 and we cross. So I made a bit of a mistake here. So the valency of nitrate is actually 1. Okay, so when we cross the valencies, lead gets a 1 and this gets a 2. Okay, so that would be the formula over there. Okay, so now here's the information again, and we have to choose from the bulleted list above to label the diagram of the setup. Okay, so very confusing. Let's break it down. Here's positive, here's negative. Okay, positive side is where we have the anode. Negative side is where we have the cathode. All right, so anode is where oxidation takes place. So here we'll have oxidation, here we will have reduction. Okay, and we can remember oil rig. Okay, so what we want is, let's just go back, we have to plate a lead rod with nickel. Okay, so one of these rods is going to be lead, one's going to be nickel. Okay, and we have to plate a lead rod with nickel. Okay, so what that tells us is immediately in the solution, this has to be our nickel nitrate solution. Okay, so that needs to be over there. We need to have this nickel nitrate solution. So I'm just going to write it as NiNO3,2, but you could also literally just write it as you see it here. Okay, so we have that, right? Because we need these nickel 2+ ions. Okay, we need this in solution. Okay, for us to plate the lead rod with nickel. And now we need to think what needs to happen to this nickel 2+, right? So we need nickel 2+ to somehow end up as solid nickel. Okay, well, to do that, what needs to happen? Nickel needs to gain electrons. Okay, because here it's deficient of 2 electrons, so we have to give it 2 electrons for it to become a solid. Okay, so and what type of reaction is this? Is this oxidation or is this reduction? Well, it's a gain in electrons. Okay, it's a gain in electrons, so that means it's reduction. So here we have reduction. Okay, where does reduction take place? Reduction takes place at the cathode. Okay, so here we know with this nickel needs to become solid nickel here. Okay, but we need to plate the lead rod with nickel. So that solid nickel needs to come on top of what? It needs to go on top of the lead rod. Okay, because we need nickel on the lead rod. Okay, so this needs to be lead And on top, right, let me actually use a different color. Okay, so this thing needs to be lead. Okay, the rod, all of this thing needs to be lead. And on the outside, we need this solid nickel. Okay, so that pretty much tells us what this thing is, right? That this will be where the lead is. Okay, the lead rod. So then obviously this would have to be our nickel rod. Okay, so that's how we would do that question there. Okay, let's move on. So 723, they say after 30 minutes of the plating process, the mass of the lead rod has increased by this. Okay, so what is this, right? We're coating it with nickel. So this is the mass of nickel that is now on top of this lead rod. So they say calculate the number of moles of electrons needed to produce this increase in mass. Write the answer correct to 4 decimal places. Okay. So what we're going to have to do is they say the number of moles of electrons. Okay, so we're going to have to use a mole ratio, okay? Because we can find the moles of nickel. And then we're going to use a mole ratio with which equation? Well, we're going to use a mole ratio with this one, okay? Because we know the mass of this, so we can work out the moles of this. So then we can use a mole ratio to work out the moles of electrons. Okay, but we need to be careful because of this mole ratio. So 1 mole of nickel atoms requires 2 moles of electrons. Okay, but let's start off with just working out the moles of nickel. Okay, so we do our standard N is M over M. Okay, so we're trying to find the number of moles. We know the mass, 1,1 grams. The molar mass of nickel, we just find this on our periodic table, that's 59. We do that calculation and we get 0,0186 mole. Okay, remember always do that while we're doing calculations to 4 decimal places. Okay, 4 decimal places. So if we do that, we now need to do a mole ratio between nickel and what they're asking, electrons. Okay, so we know 1 mole of nickel requires, well, sorry, yeah, 1 mole of nickel requires 2 moles of electrons. That's our mole ratio, and it came from here. Okay, so, and again, you could have found this formula on our standard electrode potential table. You'll see it's over here, but you can also just deduce that it needed 2 electrons, as I spoke about before. But anyways, that's where this mole ratio comes in. So here we have 0,0186 mole. So what we do is we just times that thing by 2. And what do we get? 0.186 times 2. We get 0,0372. Okay. So now we just need to make a conclusion. We say therefore the moles of electrons is 0.0372 mole. Okay. Over there. So that's what we have. So interesting 2 things here. The memo gives it to 4 decimal places. They give the answer to 4 decimal places. Oh, okay, I should have read. Okay, so they ask it for 4 decimal places. But another thing, the memo has this as, this is a 3. Okay, and the way the memo did that is they didn't use their rounded answer here. Okay, so they rounded to 4 decimal places and wrote it as 4, but then when they used this, they kept this in their calculator and times that by 2. Okay, I think they will accept both, to be honest. Sometimes it's a bit frustrating keeping this answer in your calculator. I know it's best practice, but yeah, that's where they get that 3. But if you take this answer and times it by 2, you'll get what I've shown there. You'll get this with 3,2. So yeah, that's a bit of a frustrating one. I'm not sure what they would accept. But yeah, the best practice is always keep answers in your calculator without rounding. Okay, but normally 4 decimal places saves you, but it didn't save you in this one. Okay, so yeah, just be a bit careful with that. Now for B, they say hence calculate the average current that was maintained during this time period. So we need to decide which formulas we're going to use, and these are given on our formula sheet. Okay, and I've also included the constants here because we're going to need Faraday's constant, which is that value there. Okay, so they say we need to calculate the current, which is this, okay, during this time period. So do they also give us a time, 30 minutes. Okay, so what's very important is they give us a time as 30 minutes, but what's very important is, I'm saying very important a lot, but what's very important is we need that in seconds. Okay, so that's gonna have to be changed to seconds. So we'll have a little star that needs to change to seconds. Okay, and the average current is I. So again, we need I, we have time. So we need to find Q, right? And we can find Q with this formula. So F is a constant, we know that, and N is the number of moles of electrons, which we just calculated, right? So what I'm gonna do is I'm gonna be using our previous answer, okay, from here, okay, the rounded one, so without this 3, okay. So anyways, we have that Q is equal to the number of moles of electrons, okay, so careful that N needs to be moles of electrons, all right? So what we do is we know from our previous answer was 0.372, all right, that gets times by Faraday's constant. We put this in the calculator, 372 times 96500. Okay, so we get this value here, but remember, very important, keep it in your calculator. And the units of this, so what is Q? Well, Q is charge. Okay, so you have to have the units here. Q is charge, okay. And I see immediately we're going to be getting a different answer from the memo. So that's a bit frustrating, because they obviously use this as 3. I'm just going to commit by using it as 3. Okay, I'm going to change my mind there. So I'm going to be using 0.0373, and I'm going to be getting 3599,45 coulomb. All right, remember it's coulomb because this is charge. Okay, but they didn't ask for the charge, they asked for the current. So now I need to be using that Q equals IT, where I know the charge, I just calculated it, and the time I've given, 30 minutes. Okay, so my charge is now 3599,45. I don't know what I is, but my time is 30 minutes. I just literally just say that times 60. Okay, that'll give me the time in seconds. So what we should be ending up is we take 3599.45 divided by 30 times 60. Okay, you just got to be careful how you put that in your calculator. But anyways, to 2 decimal places, we get that this is 2. The units for current, amperes. Okay, don't forget amperes for current. Okay. Now for 7.2.4, explain why it would not be possible under standard conditions to plate the lead rod with aluminium metal to form an aqueous solution of, from an aqueous solution of these aluminium 3+ ions. Okay, well, that's a bit interesting, right? But let's have a look. So we need to be looking at solid lead. Okay. We need to be looking at solid lead and solid aluminium, and we need to be looking for these aluminium 3+ ions. Okay, so because we're going to have a solution of these aluminium 3+ ions, and then we're going to be having a lead rod, right? And we're going to be trying to coat that so with aluminium metal. So what we need is we need to think, okay, we have to have aluminium ions, okay, and we need to then coat the lead rod with aluminium metal. So this has to undergo reduction, all right, to become aluminium metal. Remember, this will be solid. Okay, so now we have to have a look at, yes, once again, the standard electrode potential table, and we need to be analyzing. So let's look at, here we have lead. Let's see what's happening with lead, and let's see where do we have aluminium. Here we have our aluminium ions. Okay, so let's have a look. Let's have a look at that. All right, so we need let's also just analyze what we have in solution. Okay, let's just analyze what we have in solution. So let me move this down a bit. Okay, so in our solution, right, it's an aqueous solution, so we are going to have aluminium ions, and it's aqueous. We are also going to have water in our solution, right? This will be our solution. Okay, here's the walls of our container. So we look at what's in our solution. We need to see, okay, what's competing over here, right, to be reduced. Okay, so that was not what I had here, because we won't have lead ions, we'll have solid lead. Okay, so we're looking at things that are competing to be reduced, because this needs to be reduced. Okay, and the thing that will be reduced means it will be the strongest oxidizing agent. Okay, so what we're doing is we're looking between aluminium and water, aluminium ions. So the strongest again, the strongest oxidizing agent will be here at the bottom. Okay, so remember the arrow is pointing to the strongest one. Okay, so what we'll look is aluminium's all the way up here, so it's a very weak oxidizing agent. Okay, and what it's competing with is water. So let's have a look. So if water is above, that would mean that aluminium ions, these aluminium 3+ ions, are a stronger oxidizing agent. But you'll notice that's actually not true, because if we look, water, so here we have water, but this is with oxygen gas. We don't have oxygen gas. Okay, so this can't happen. So we need another one with water. Here's water. Okay, here's water being reduced. Okay, so here water is a stronger oxidizing agent. So what's going to happen is water is actually going to be reduced instead of our aluminium. Okay, so that's going to be a problem. So we won't be able to coat this lead rod with aluminium metal, because this is not going to happen. Okay, because it is a weaker oxidizing agent than water. So water is actually going to gain electrons, okay, according to this reaction here. Okay, we're going to actually be producing hydrogen gas instead of aluminium metal like we wanted. So that is literally what we're going to write. We're going to say that, well, water, okay, so this is where I'm going to answer over here the question. And this was just some explanation. So water is a stronger oxidizing agent than the aluminium ions. Okay, well, so that means that water will be reduced and not the aluminium 3+ ions, which is what we want to reduce, right, and not these ions. And that's what we want to reduce, because if those are reduced, right, so if these ions are reduced, well, then we get our solid aluminium metal. Okay, but that's not what's going to happen. So water is a stronger oxidizing agent than those aluminium ions, and H2O is going to be reduced at the cathode and not aluminium 3+ ions. Okay, now question 8. All right, I should have had question 8 up here. I don't know why it's not there, but anyways, question 8. Now we're this is organic chem. Okay, we're in organic chemistry now. So the saturated hydrocarbon C5H12 reacts with Cl2 as shown below, and we have to state the general type of reaction over here. Okay, so this is a substitution reaction. Okay, so be careful. Only alkenes, right, so unsaturated hydrocarbons, can undergo addition reactions. Okay, so here we have a saturated hydrocarbon, so this is not an addition reaction, and it's also not an elimination reaction, so it has to be a substitution. Okay, so substitution, how do we spell that? Substitution. All right, so again, I don't help with English. Okay, and yeah, okay, anyways, so it's a substitution. Remember, the general type of reactions is what we got: substitution, addition, elimination, and condensation, right, or also known as, well, esterification, condensation. Yeah, over here, explain the meaning of the term saturated hydrocarbon. Okay, so this is again just a definition, right, for 3 marks. So a saturated hydrocarbon. So first we need to be talking about hydrocarbon. So hydrocarbon means that it's a substance that contains carbon and hydrogen only. So only carbon and hydrogen. Okay, that's hydrocarbon. And then for saturated, this part over here, we need to say that all carbon to carbon bonds, okay, so the memo says carbon to carbon, like this. So all carbon to carbon bonds are single bonds, okay. So there's other ways you could have worded this, but yeah, so hydrocarbon, it's in the name, hydrocarbon, so it only contains carbon and hydrogen. And saturated means that we only have single bonds, there's no double bonds. Okay, perfect. Now they give the reaction there again, and they say in one experiment 45 grams of that, well, to be honest, that is pentane, so 45 grams of pentane reacted. Calculate the volume of chlorine gas at STP. So STP, we're probably going to be using molar volume, maybe, needed to react with all the C5H12 to form that over there. Okay, so, well, mole ratio type stuff, right? When in doubt, mole it out. They give us a mass here. Let's just work out the moles of this. Okay, and then we're going to try get the moles of this. All right, and then convert that to a volume. Okay, it's just the classic. You have a bunch of things like mass, volume, whatever. You work out moles, use a mole ratio, work out moles, and there you can go concentration, volume, mass, whole bunch of other stuff. Okay, so that's our general process. So what we're going to do is we're going to be saying, well, for C5H12, moles is equal to M over M. They give us our mass of 45. Our molar mass is 5 times 12 plus 12 times 1. That is going to be 72. Okay. And for that we get 0.625 mole. Okay, now what we do is we have to do a mole ratio between C5H12 and Cl2, okay, because they're asking for chlorine gas. Remember, this is not chlorine gas. Okay, so if we do the mole ratio there, we have 1:2, and we have 0.625 of this, so that means we're just going to double that. 0.625 times 2, that very nice and conveniently is this. Okay, so we have the moles of chlorine now. Okay, but they don't ask for the moles, they want volume. So now what we're going to be doing is we're going to say the number of moles is V over Vm. We can use Vm because we are at STP, so we have that going for us. We know the moles of chlorine gas, so let me just say we're working with chlorine here, chlorine gas, and volume we're trying to find, and volume at STP is 22.4 decimeter cube. Okay, per mole. Okay, so anyways, when we do this, we find that the volume is equal to 28 decimeter cubed. 28 decimeter cube. Okay, don't forget your units. It's a volume, so it is in decimeter cubed. Okay, so we have that. They say the percentage yield of the reaction was 76%. Calculate the mass of that was obtained. Okay, so on this side, they're asking for this thing over here. So the percentage yield is actual over theoretical. Okay, so percentage yield is, so percent yield is actual yield with an L over theoretical yield. Okay, so we can do this on a mass basis, right? So if we have our theoretical yield and mass, then this thing out here will be output as mass. Okay, and that's good for us because I want the mass of that thing that was obtained. So how do you find the theoretical yield? Well, that's pretty easy. We just use the mole ratio. Okay, so they're asking for this, so we'll do the mole ratio of the thing we know, which is this H12, and compare that to the moles of this thing, which we don't know, but what we want to know. And we want the moles because we want to convert that to mass and put in our theoretical yield. But anyways, it's 1:1. So we use our 625. I said point, I wrote a comma. 0,625. So now we have the moles of this thing. All right, that's convenient because now we need to find the mass of this thing, this theoretical yield mass. Okay. So let's just talk about at this point theoretical. So this is theoretical, right? So 1 mole of this creates 1 mole of that. Okay. So that means we are capturing all of this when this reaction takes place. That's not always true. Okay, we cannot capture all of it. So the actual yield, right, because we're losing some of this in a whole bunch of different ways, it's always going to be less than the theoretical. Okay, so whenever we pretend if everything we use turns out to everything, so if we pretend, or if we assume rather that all of our reactants get turned into all of our products, right, with no losses, that's a theoretical yield. Okay, but we see here it was 76%. Okay. So that's why we normally use this 1-to-1, but in this case it's not exactly true, right, because of the yield. But anyways, we need this, okay, because we now need to convert those moles into a mass. Okay, so again we're going to use Old Faithful. N is m over m, n is m over m. So we know 0,625 is equal to, we're trying to find mass, right? Because we want to put the mass in here to then find a mass over there. Okay. And what we can do is use our periodic table, and we'll find the molar mass of this thing over here is 141. Okay. So that then gives us that our mass, our theoretical mass, is, if I put that in the calculator, 0.625 times 141, that gives us 88,125 grams. Okay, that is nice because we can then put that in here. Okay, and what's also nice, because here we have our percentage yield. Okay, so we know this, we now know this, so we can find our actual yield mass. Okay, that's what they want. So we're going to have that 0,76, right, or 76% is equal to our actual yield over our theoretical, which is 88,125. Okay, so if we solve for that, we'll get that the actual yield is equal to, so we take our answer times it by 0.76, and we get, we'll put it to 2 decimal places, 98, and the units, grams, mass, grams. This was in grams over here, that was grams, so our answer ends up in grams. They now give us this molecule and as a possible product of that reaction, and it says it has a structure below. We have to give the IUPAC name for this compound. Okay, so first let's identify, we got these 2 chloro groups over here, and we also need to identify our longest chain that has these. Okay, so if we start on here, 1, 2, 3, 4, well then our chlorines are on 2 and 4. Okay, so that gives us a number of 6, but if we count the other way, if we count this way, 1, 2, 3, 4, our chlorines are on 1 and 3. 1 plus 3 is 4, and because that's a smaller number, that's our correct numbering over here. We have to go across here because this is our main group here, right? This is one of our halogen, what do they call it? Halo alkane groups over here. Okay, so to name this thing, we kind of have to identify. So our longest chain is 4 carbons. So we know it's going to have the prefix bute, and we are also going to start with chloro, right? But also very important, there's 2 chloros, so it's going to be dichloro. So we're going to start with that, and we also have this methyl group over here. Okay, so let's get into it. So it's 1,3. Okay, and then we have to put at a dash, and I'll say dichloro over here. And now we need to be putting our methyl group, and to do that we're going to have to say -2, okay, because our methyl group could also be in other places. But anyway, we say -2, and then we have to put a dash because now we're going to be saying methyl. Okay, now we don't need a dash or space because it's just another word, and we say butane, butane. Remember, but is prefix of 4, and ane is because it's a alkane, halo alkane. Okay, so that's the name, 1,3 dichloro 2 methyl butane. Perfect. They say write a balanced equation for the complete combustion of this thing. Does that relate to what we had before? No, they're talking about this thing now in general. Okay, but anyways, so C5H12. We need to know what a combustion reaction is. It's a reaction with oxygen to produce water and CO2. I'm going to put CO2 first. CO2 and water. Okay, so first step with these guys, you're gonna struggle if you don't balance the carbons first. Balance the carbons first. Okay, I'll even write it here. Balance carbon first. Okay, balance carbon for how many on the left? 5. How many on the right? 1. Fix that. 5. Perfect. That is great. Okay, that is not bad at all. Okay, super easy fix. Now we need to balance the hydrogens. Do not balance the oxygens next. You are going to struggle. So balance the hydrogens. Okay, so here we have 12. Here we have 2. How do we fix that? 6. Then third step is obviously we have to balance the oxygens. Balance oxygens. Here we have 10 and 6, so a total 16. Here we have 2. We fix that with an 8. Okay, these combustion reactions should not be taking you a long time, and they should not be very tough if you follow this 3-step process in these steps. Okay, you're going to struggle. It's going to be complicated otherwise. There are other methods that are maybe a bit different to this, but also easy. This is the one I prefer. Quite simple in my opinion. We don't have to be timesing by 2. We don't have to have fractional things because there's methods where you get like 2,5 here. Don't like doing that. Okay, anyways, let's move on. Structural isomers of that thing are possible. Remember, that thing's pentane. So define structural isomers for, so alle SAGs, we get this. Compounds having the same molecular formula, but different structural formula. Okay, so you'll see this part, it's the same molecular, but different structural. So the structural word is in your definition. Okay. Anyways, for B, write the condensed structural formula of the isomer of pentane with the most possible branches, alkyl substituents. All right, actually I can speak today. Anyways, let's draw pentane. All right, just normal pentane, and then we're going to be looking at where we can move branches. Okay, where we can draw branches. So here's pentane. I'm not going to fill in the hydrogens. Here's pentane. Okay, so let's think where we can put branches. Well, we won't be able to put a branch here, right? For example, we won't be able to have C, right? I mean, that's not possible because it's literally the same thing. It's literally what we have there above. It's still a branch of 5. Okay, so it's not a branch. It's not a branch. It is part of our chain. Okay, so let's think, how about we move a carbon here? Okay, now we have at least one, so it doesn't matter if you count this way or if you count this way. Our longest chain is 4, so we have at least one branch, right? And these will just all be hydrogens, and obviously there will be hydrogens. Well, let's see, maybe I can put another branch. How about, let's see if I put a branch here. Well then, again, it's not really a branch because my longest chain is 4. Interesting. Okay, how about if I put one here, a carbon here, my longest chain is 4 over there. So if we go back here, how about we get rid of this fellow over here. We know we can't put it there because our chain will still be 4. We can't put it here, right, because our chain is still going to be 4, so we're going to have to put it in the middle. We are going to have to put it there, because now what have we done? We've changed our chain. Okay, so we've changed it from 5. Okay, we changed it down to 4, but we're trying to see, can we maybe change it smaller? But you'll see this is the smallest. Our chain is 3. Okay, our longest chain is 3, no matter which unbroken chain is 3, no matter which way you look at it. So here you go. That is where we have the most branches. Our most branches are 2. Okay, we can have 2 methyl groups over here. You are not able to have an ethyl group because that will still be, for example, if I add a carbon here, well, now my longest chain is 4. So I don't really have an ethyl group, I just have 1 methyl. Okay, but what I have to do now is I have to write a condensed structural formula. So I like to do these left to right. So we're going to have CH3, okay, and then we're going to have this carbon. Okay, so I'm going to say, all right, well, I have a carbon. On this carbon, okay, I have 2 of these groups here. Okay, on that carbon, and then after that carbon, I have just a normal CH3. Okay, so here you would have the condensed structural formula. I have CH3 over here. Here's my CH3. Then I have this carbon. Okay, that's a carbon there. I say, what is on that carbon? Well, this thing's on that carbon, and this thing's on that carbon, so 2 of them. And this thing is also then attached to that. Okay, so that's the condensed structural over there. We now need to define a functional group by looking at the compound pent-1-ene. Okay, so now we're looking at an ethene. So a functional group, it is a definition from the SAGs. So it's an atom or group of atoms that form the center of chemical activity in the molecule. Okay, so functional groups, for example, we have hydroxyl, we have carboxyl, I think that's the word. Hydroxyl, we have that haloalkane type thing, halogen, right? That halogen area, and also have alkyl groups, right? But anyways, they say draw the structural formula for the functional group of pent-1-ene. Okay, well, this is just double bonded carbons. Okay, double bonded carbons. That's what makes it an alkene. Okay, how do we know? Double bond. Okay, so we just draw that. They said functional group of an alcohol. Well, we would draw an hydroxyl group like this. Okay, but that's what we have there for the functional group. They say write the condensed, so here we have to do this condensed thing again, of a positional isomer of pent-1-ene. Okay, so again, I like to draw these. So currently pent-1-ene is this thing. There, 5 carbons. That's currently pent-1-ene. Well, let's see, can we put this double bond in the, we need to be careful. Okay, we need to be careful. So let's count how many hydrogens we have here. Like this. Okay, remember every carbon can only have 4 bonds. Okay, so be careful of that. Anyways, we should have 2, 4, 6, 8, nearly messed those, 10. Okay, so, but we could have used the general formula anyways. So we know it's C5H10. So whatever we do, we move this double bond, we need to still end up with this. Okay, because remember, positional isomer, same molecular formula, just the different position of the functional group. Okay, so again, isomer, positional isomer, our definition will have that word in it. Okay, but anyways, we need to try and move this double bond. Well, let's move it just 1 across, why not? See what happens here. So again, 3 hydrogens there, there, that only has 1 hydrogen. This will also only have 1, and here we have 3. Okay, well, let's look at this. We have, I'll count in 2s again, 2, 4, 6, 8, 10. All right, so that's a possible one. Now we just need the condensed structural formula. Well, let's work left to right. So we have CH3. Okay, then I have a CH. Okay, this carbon has an H. Then this carbon has an H. So I write CH. And this carbon has 2 H's. So I write CH2. And then this carbon has 3 H's. CH3. So there we have our condensed structural formula. Okay, cool. Now we need to answer true or false. Dimethylpropene is a chain isomer of pent-1-ene. Okay, so we need propene, okay, to have 2 methyl groups on it. Okay, so propene is going to look like this. All right, and remember it's propene and prop is 3, so we have this thing. All right, and on top of this somehow we need to be having two methyl groups. Is that possible? Let's see. So the methyl groups will be here, no? So let's have a look at that. So that will have carbons there, there, and there. Hydrogens, rather. So this is possible. We just got to check the chain. So the longest chain is only 3. And remember, we have to include our functional group. So our longest chain is 3. Okay. So this is possible. Okay. For example, there. And over here, we have 2 methyl groups. Okay. But we just got to make sure, so a chain isomer has the same molecular formula, and different length of chain, different chain length. So we got to make sure that this thing is C5H10. And you'll see there's 5 carbons. And in terms of H's, 2, 4, 6, 8, 10, 11. Okay, so that is not possible. False. All right, because we have 11 hydrogens. The formula for this is C5, whoops, H11, right? 2, 5, 8, 11. Okay, so it was close. It was close, right? But no, it's this and this are not the same, right? So this is unfortunately not, or fortunately, who cares? If you got the right answer, it doesn't matter. Okay, but it's not. It's false. Not true. 8.2.5. Methyl 2-butane is a chain isomer of pent-1-ene. I say that as a fact now. We don't have to be checking true or false. Which of these two compounds will have the higher boiling point? Okay, so let's figure out. So pent-1-ene is just this thing, right? So it's unbranched. Okay, it's unbranched. Not going to draw the hydrogens. Methyl butene. Okay, so but is 4. Okay, and on the second carbon we have our double bond, and we have methyl. Methyl will have to be, our methyl group will have to be here, no? Yeah, our methyl group will have to be there, and we have this. Okay, but the main idea is, look at these two chains, right? Let me fill in these hydrogens up here. Hydrogen, 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 hydrogen. Okay, so they have the exact same number of electrons, right? Because they have the same hydrogen, same number of carbons. Okay, there's an H, 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 H. No H is there. H, 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 H. Okay. So 2, 4, 6, 8, 10, 11. So that's got 11, which is problematic. What did I do wrong here? This one, not going to have a hydrogen here. Okay. Well, that one's got 10 hydrogens at the top. This has got 2, 4, 6, 8, 10. Okay, so they have the same molecular formula, same number of electrons. So we need to identify what's going on. Do they have different types of intermolecular forces, or what's going on? So they both have London, okay? But the thing is, this thing here at the top is unbranched, whereas this thing here at the top is branched. Sorry, at the bottom is branched, top unbranched. So it's going to be tougher for molecules, right, of here at the bottom, this methyl 2-butene, to come into contact, right, and kind of attract each other. Okay, so it's almost like, imagine you're playing Tetris. It would be a lot easier to Tetris stack the ones in red than Tetris stack the ones molecules of green. Okay, and molecules need to come close to each other, so those induced dipoles can be formed and the electrons can interact, right? So if we look at this 825, because, okay, we don't even have to, we can just say which, we don't have to explain. So I'm going too deep in here, but which one of these will have the higher boiling point? We need to say, okay, which, the higher boiling point means the one that will have the higher, while stronger intermolecular forces. So the one that will have stronger intermolecular forces is this one here at the top, this pent-1-ene. Okay, and it's because it's unbranched, so there's a larger interacting surface area. So that means that there will be stronger induced dipoles, and therefore it will have stronger intermolecular forces, more energy required to overcome the stronger forces. Therefore, pent-1-ene will have a higher boiling point. Okay, So that is how you would answer it in those bullet points if they asked for it, but thankfully they didn't, just 2 marks. Question 9. Ethanol is a very useful compound. It's a universal solvent. It can, so things that are polar can dissolve in it, things that are non-polar can dissolve in it. That's why one of the reasons. It can be produced by several different reactions. Name the functional group of ethanol. We just gave the definition of functional group earlier, so we should know this. Well, if you didn't know it here, that's a bit tough. But that forms the center of chemical activity, right? And it's an alcohol. That means it's hydroxyl. Hydroxyl. Okay, they don't ask you to draw the hydroxyl, don't do that. They asked you to name, that's why it's in bold. 9.2. One example of a reaction producing ethanol is given below. So we have glucose over there, yeast fermentation. We are producing ethanol and carbon dioxide. The products of this reaction have a similar molar mass. Explain why ethanol is liquid at room temperature while carbon dioxide is a gas. Okay, so we need to identify, so this is one we're going to have bullet points. Okay, first thing we need to talk about the type of intermolecular forces. Okay, ethanol has what type of intermolecular forces? Has hydrogen bond forces of attraction. Okay. All right, why is it hydrogen bonds? Remember, hydrogen bond forces of attraction, I think we spoke about it earlier in this paper, is when hydrogen is bonded to one of these, and one of these things have a lone pair of electrons. You'll see that is true because you'll have carbon bonded to an oxygen, bonded to an hydrogen, but oxygen will still have these 2 lone pairs here that another hydrogen can come and be attracted to, okay, in another molecule. This isn't a bond, this hydrogen is from another molecule. So ethanol's hydrogen bond forces of attraction, and carbon dioxide, probably better if you just said CO2. Yeah, I'm just going to say CO2. And CO2 only has London, okay? London forces of attraction. London. That's how you spell London, right? Surely. Then I just embarrassed myself now. London forces of attraction. London forces of attraction, or intermolecular forces. Okay, so CO2, well, we had to do a bit of investigation. So CO2, the bonds in CO2 where carbon's bonded to oxygen, this is a polar bond. It's a polar bond because their electronegativities are different, but the molecule is linear. The molecule is linear, so the molecule is symmetrical. So the molecule is linear and symmetrical, so the molecule is non-polar. Non-polar molecules has to have London forces of attraction. Okay, perfect. So we have that. Now we need to be talking about the relative strength. We spoke about the types. So this comes up all the time, guys. You need to know how to answer these questions in terms of boiling point. This is essentially boiling point type question. All right. So we spoke about the types. Now we need to talk about the strength. Which one is stronger? It's getting a bit boring, right? I don't know why I'm using that intonation, but anyway, hydrogen bonds are stronger than London forces. Do not write then. Then is when we talk about time. Than London forces. Okay. Now we just say, and we literally quote this, we quote the Sags. Therefore, more energy is required to overcome. Was a close call. Overcome the stronger forces of attraction. Forces of attraction. A lot going on here. It's a bit boring, right? We've done this so many times and you knew exactly all the bullet points before I was writing them. Hopefully. More energy required to overcome the stronger forces of attraction between molecules of ethanol, or ethanol molecules. Ethanol. Now we need our conclusion. Therefore, So yep, it's therefore ethanol. Ethanol. Did I spell that wrong? I can't spell that wrong. It's right there. Okay, ethanol is a liquid at room temperature. Okay, that was bad. Liquid at room temperature. Sorry, I've been sick. I don't know if you can tell by my voice. Sick and tired. Mostly sick. Okay. Ethanol is a liquid at room temperature. Surely that is how you spell liquid. But yes, so we have that. Same old bullet points. You can and should memorize these just like Le Chatelier's. You identify the change, the stress. You say how the system is going to change. You say which reactions favored and why to counteract the stress. Therefore, the yield of this increases, concentration of that increases, etc., etc. Okay, these bullet points come up all the time, guys. So learn them. Two other reactions by which ethanol may be produced are shown below. Ethene plus A, and we have the phosphoric acid gives us ethanol. Okay, what is this thing? Ethene. So I hate organic reactions, guys. I hate memorization. Organic reactions, what are they? Memorization. Anyways, this is, so we make our lives easier for us. If you want to be lazy, you got to make it easy. Okay. Anyways, ethene is an alkene. So it is unsaturated, right? So when we have unsaturated compounds, they undergo addition reaction. So we know here this is some addition reaction. Okay. B, we don't know what it is, but it goes with potassium hydroxide, heated under reflux, and then it produces ethanol and KCl. Where did the C come from? Well, this thing over here has to have had a chlorine in it. Okay, so this thing was probably a halo alkane. Okay, probably a halo alkane, because where the heck did the C come from? Okay, so let's have a look. Identify reactant A. So ethene plus A gives us ethanol. So ethene before didn't have oxygen, but now ethanol has oxygen. So what is a common thing that has oxygen that we use in organic reactions? Water, steam, H2O. Okay, then for 9.3.2 they say give the IUPAC name of compound B. Well, this thing here on the left was a haloalkane and it had one chlorine, so it has to be chloroethane. All right, so luckily there wasn't much memorization there, but oh no, specific reaction types, reaction 1. Okay, so these are annoying because there's like hydrolysis, hydration, things like that. Okay, this is where the memorization comes in. Okay, but here if we're literally adding water. We are adding water. That is hydration. Okay, think about if you're thirsty, we don't drink Prime, unless you want to, who cares? But we drink water for hydration. Okay, number 1 hydration drink since before 2000 BC. Hydration, water. Anyways, reaction 2, the specific reaction over there. We're changing it into an alcohol by giving it oxygens. Okay, so this is hydrolysis. Okay, well, let me fix my spelling there. Hydrolysis. Okay, I kind of just figured this out now, but right, we're giving it an oxygen. Okay, because this thing before, I'll show you, it was C, these are hydrogens, and then it had a chlorine somewhere, right? But then what happened is we got rid of this chlorine and it became an oxygen, right? Because now we have ethanol. So hydrolysis, what did we add? We added an O. Okay, maybe that's the way you can remember it. Okay, yeah, anything to help with memorization, because memorization is annoying. Anyways, here, ethanol can be used to prepare the compound ethyl hexanoate. What is that thing? It smells fruity. All right, so it's an ester. Okay, esters have that aromatic smells, and also ethyl hexanoate, we know that's an ester. So name the homologous series to which ethyl ethanoate belongs. It is an ester. That is the homologous series. Give the IUPAC name of compound X in the above equation. So we have ethanol plus X gives us ethyl hexanoate. This has to be a carboxylic acid, and it has to be hex, and it has to be an acid. So it is hexanoic. Spelling good. Acid. Hexanoic acid. Perfect. 2 marks there. You can't just say hexanoic. You need hexanoic acid. So you need to know it. Know it. Alright. Sorry. Identify compound Y in the above reaction. Well, esters, we produce water. Okay, that's why we need you need to have a dehydrating agent. That's why I think we normally use acid for these ones. Yeah, that's actually exactly what this catalyst over here. Identify suitable catalyst. Well, this is just from theory. You need concentrated sulfuric acid. Okay, sulfuric acid. So you could also just write sulfuric acid. Phosphoric acid is also okay. It's allowed. All right. Now 945. Last question for the exam for 200 marks in total. Give the IUPAC name of the straight chain functional isomer of ethyl hexanoate. Functional isomer is the same molecular formula, okay, but it has a different functional group. All right, so we should know from series that esters are in the are functional isomers of carboxylic acids. Let me say that again. Esters are functional isomers of carboxylic acids. Okay. But let's figure out. So ethyl, how many carbons in that? 2. Hexanoate, how many carbons? 6. Hexagon. Okay. So we need a carboxylic acid that has a total of 6 plus 2, 8 carbons. 8 carbons. So if we have a carboxylic acid with 8 carbons, spoiler alert, octanoic acid. All right. Octanoic acid. So there we go. Chemistry. Hopefully we've taken the mystery out of chemistry. I probably said that before. Anyways, all the best. Thank you for watching, and I wish you well.